And from the yesterday chat box comments, many of our young researchers, they actually asked how they can start their research in mathematical biology. They need support, they need collaboration. So it's a good sound.
Yes, yes, that's very good. So I'd like to request Professor Osman Goni sir, could you please record all the sessions today? Because Dr. Kamruzzaman will be busy today because he will chair the session. And our media partners are also actively working to cover the news of the conference.
Yeah. They are so much active.
Dr. Kabir, you said I need to record whole program.
Yes, please, session by session, just session 1, session 2, session 3. When session 1 starts, just record, and when it stops, you just stop the recording, and for the next session, you will start again the recording.
Okay.
Please, okay, thank you very much.
Is there any news in the daily newspaper today?
Yes, the Shamukal, in the Shamukal and New Age, you can find Shamukal. They have they wrote many things about the conference. And in the Jamuna TV, maybe last night they broadcast the news of the conference in their news bulletin.
Yeah,
That's good.
yeah, they broadcasted 7 p.m., 10 p.m., 12 p.m.
I see. So maybe tonight they will also broadcast.
Yeah, to ignore the complexity, even you can just start the record until the end of the all session. Then just if necessary, you can edit the video before upload on our website. Yeah, sometimes.
Yes, and it is also live streaming in our YouTube channel, BSMB YouTube channel.
আমাদের মনে হয় 2-4-5 মিনিট পরে শুরু করতে হবে কিনা পার্টিসিপেশন তো এখনো
I think they will. I think
still we have 5 minutes left. So
okay.
Still 5 minutes. Yeah, we can see.
Still we have time.
Professor Philip, can you hear me?
Yes, hello.
Okay,
Hello.
very glad to see you.
And nice to meet you.
Yes, so and
nice
warm
to meet you
welcome to the conference.
Thank you. I'm sorry I couldn't join yesterday. I had another conference, so sorry about that.
It's all right.
Okay,
it's all right. Thank you very
That's
much.
okay.
So let me introduce is Professor Philip Maini from University of Oxford, and Professor Philip will talk today in the last session.
How's the conference been going?
Sorry?
How the conference is going well?
Yes, it's fine. Yesterday there was 3 sessions, 3 speakers, and today we have 4 sessions.
Yeah.
And we hope today it will also be fine today. We hope. And thank you very much for joining, because I know you have very busy schedule. However, you have managed some time to give a talk here.
Oh, well, no, thank you for the invitation. Very kind of you. Thank you.
Yes. Okay. Welcome. Thank you very much once again.
I will have to say it's the earliest I've started work on a Saturday, but that's okay.
Yes, it's all right. It's all right. It's all right. So now you are in Oxford now?
Yeah, in the office, yeah.
I see. Okay.
So it's 9 o'clock here in the morning.
I see. Yes, 9 o'clock. Yes, 9 o'clock in the morning. Today, our first speaker is Dr. Katrina from Cardiff.
Yep. So that's at 9 o'clock, isn't it? I think.
Yes, 9 o'clock. 9 o'clock.
I'll just go and get a quick coffee then before.
Yes, please make comfortable.
Yeah.
Thank you. ফিলিপের গত বছর ওনার 60তম জন্মদিনে কনফারেন্স ছিল অক্সফোর্ডে।
Oh,
জেডি মুরে সেখানে আসছিলেন, আমিও গেছিলাম, আমার পোস্টার প্রেজেন্টেশন ছিল। তো ওখানেই পরিচয় ওনার সাথে আর কি। এর আগে ইমেইলে বা ইয়েতে পরিচয় হয়েছে, ফিজিক্যালি দেখা হয়েছে গত বছর। আর জেডি মুরের সাথেও দেখা হয়েছে। তারপর ক্যাটরিনা এবং কেভিন পেইন্টারের সাথে এর আগেও জাপানে দেখা হয়েছে।
Yeah, it's a good strategy, Dr. Humayun Kabir. We can also follow, sometimes they sometimes even publish a special issue in their journal. Some of the famous scientist birthday, right?
Yes, it is very common practice in the international arena.
Yeah, so for our community, for our society, we can also start in near future.
Yes, of course. Professor Kim, can you hear me? Professor Youngjung Kim, can you hear me? So, how are you?
Okay, I can hear you. Hello.
I'm very glad to see you after a long time.
Yeah. Nice to meet you again.
Yeah. Thank you very much, and thank you for joining.
1 second. I want volume. How is my voice? Can you hear my voice clearly?
Yes.
It's okay.
Yes, it is loud and clear.
Okay, that's good.
Okay, so it's really great pleasure to see you after a long time, and thank you for accepting our invitation.
Thank you very much for the invitation. I'm very glad to give a talk here.
Okay, thank you very much.
I tried to change. I don't know. I tried to change my name in English here, but somehow here in my Korean character. So
I see. It's all right. If you can, it is all right. It is all right.
Clear and understandable. It's clear, I think.
There should be a way.
সমীর দাদা শুধু শুনতে গেছে, আমাদেরকে কিছু বলছে না। গুড লিসেনার। Good afternoon.
Good afternoon.
You all are doing well.
Thank you. We hope you are also doing well.
Thanks. So far it's okay, and I joined yesterday. The conference is really good. I mean, it's a good planned conference.
Thank you very much.
Yeah, we are also happy to see you yesterday and today as well.
And yes.
You see, here we have many participants compared to the normal conferences. I mean, I think this sort of conference will be popularized soon.
Yes, maybe this is one of the positive impacts of COVID-19.
COVID, exactly. People will stop traveling.
Yes. Anywhere of the world, you can easily join.
Lot of foreign country, I think. Yes. Morocco, Egypt, Lebanon, Iraq.
Yes.
Japan, yes.
18 countries, about 19 countries.
It has a true international flavor.
Yeah, exactly.
Also, we can see Shomir in television and newspaper also.
You can see myself on television.
Yes. Television, yes. And also newspaper.
Oh, I can understand it now. It's your connectivity, right?
No.
Yeah, correct. You're right. The pressure is.
Professor Philip is here also.
Yes, yes,
Yeah.
yes.
Yes,
We just
join.
welcomed him.
Thank you.
Nice to
Mamoon,
see
good
you.
afternoon. Your mic is off.
Mamun sir, your audio is muted. Please unmute
I'm
your
fine,
audio.
thank you. And you?
Yes.
I'm
now
fine,
okay.
thank you. I
So,
saw you after a long time.
Yeah.
thank you very much for
Very much.
joining, sir.
Okay. Thank you.
So, Mayan, so you have to take photo like this.
Yes, yes.
Yes,
Okay, let me take.
but my screenshot does not work.
I'm taking.
Yeah, okay, okay. Email.
Sir.
I receive email from Professor Saleh Tanvir.
Okay.
So it's okay for him.
Okay. So
Yes,
I
at
think
10,
by
7.
3 days we will call for a meeting and sit together and finalize our program.
Okay,
Yes,
our
yes.
first speaker will join within 2 or 3 minutes. She sent an email, so hopefully she will join with few minutes.
Okay.
Humayun,
Yes?
Hello.
I think,
Good morning.
good morning.
Good morning. Very nice to see you, Dr. Katrina, and
Thank you.
thank you very much for joining. And once again, I'd like to thank for accepting our invitation.
Thank you very much for inviting me. It's an honor
Most welcome.
really to be part of this a very prestigious panel. And yeah, I wish all the best to Bangladesh for mathematical biology. I guess I should get started because you are on a strict schedule. I was joining with my Zoom and then it asks for an update. So sorry for the.
It's all right. It's all right.
Yes. So okay, so I'll just dive
Okay,
into
so formally we can start now. So Professor Haidarali Bishwas, shall we start?
Yes, I can do. I think it is not 6.
It is 6. Okay.
So okay, I think we can start now because
Okay.
all our speakers are now available here.
Yes,
and
yes.
the participants almost 54. So we'll just start and then continue.
Okay, thank you very much. Respected President of Bangladesh Society for Mathematical Biology, eminent keynote speakers, distinguished scientists from home and abroad, ladies and gentlemen, Assalamu alaikum and very good afternoon, very good morning and very good evening to everyone because it is International E-Conference. This is Dr. Mohammad Humayun Kabir, Secretary of Bangladesh Society for Mathematical Biology. I take a privilege to warmly welcome all of you to the second day of the International E-Conference on recent advances in biomathematics 2020 with the theme Biomathematics to combat the threats of mysterious pathogens. Today, we feel truly honored and privileged to have a galaxy of eminent mathematical biologists with us from different corners of the world. So we would like to start our scientific session now. So this session is chaired by Professor Dr. Pavel Shariar, Shahjalal University of Science and Technology, Bangladesh. The speaker of this session is Dr. Katrina Kauri, School of Mathematics, Cardiff University. So before starting the session, I'd like to take the opportunity to extend my sincere thanks and gratitude to Dr. Katrina Cowrie for accepting our invitation on behalf of the society, and on my personal behalf, I would like to extend my sincere thanks. And I know she has very busy schedule, but however, she managed some time to give a talk here. That's why I must thank her and pass our sincere gratitude to her. Okay, now I'd like to request Professor Dr. Pavel Shahriar to conduct this session. Thank you. Now over to Professor Dr. Pavel Shahriar.
Thank you, Dr. Humayun, and welcome to the second day of International E-Conference on Recent Advances in Biomathematics. I would like to welcome you all. In this day, we have 4 speakers, keynote speech they will deliver to us. And we open today with Dr. Katrina Cowrie. She's from School of Mathematics, Cardiff University, United Kingdom, and our title of the talk is Mathematical Biology Across Scales, from fertilization and embryogenesis to COVID-19 modeling. Before we use Dr. Katrina a bit, Dr. Katrina Cowrie is currently a senior lecturer, associate professor in applied mathematics at University of Cardiff, University of Oxford. Her research interests involve deterministic and stochastic mathematical methodologies to solve cutting-edge challenges in biology, engineering, and physics, but also in business and society. Her current focus in mathematical and computational biology, modeling of fertilization and embryogenesis, with a particular interest in calcium signaling and its interplay with cellular mechanics. From 2015 to 2019, she was a core member in European Union funded Mathematics for Industry Network. 32 countries are involved in this area, and she continued to actively involve in European industrial maths activities. From 2017 to 2020, she was a core member of the H2020 cshop.eu project, where 18 organizations in 12 countries worked closely with society on pressing social challenges. Dr. Katrina has given many invited lectures all over the world. She also published a good number of very well received expository papers and monographs related to mathematical and computational biology. So it's time to welcome Dr. Katrina to deliver her lecture today. So Dr. Katrina, it's up to you now.
Thank you. As I said before, it's truly an honor to be here. I am going to dive into my presentation now, so I will share my screen. So just a minute. Is that visible?
Yeah.
Yes?
Yeah.
Yes, 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 yes.
Okay, that's great. Sorry, put it in the presentation mode. So as it was mentioned already, I am a senior lecturer in applied mathematics at the School of Mathematics at Cardiff University. And I'm going to talk today about mathematical biology across scales through taking you through a summary of some of the projects I have been working on with other collaborators in Cardiff and elsewhere. And as it was mentioned, I'm working on fertilization and embryogenesis mostly in the last few years. And more recently, we also dived into COVID-19 modeling like so many modelers around the world. And with this, I would like to give you the outline of this talk. So I'm going to talk about a very interesting challenge and a very important challenge for the society, which is to understand better in vitro fertilization. This has to do with modeling in various scales, so I'll explain that later. And then I'm going to talk about calcium signaling and mechanics, both in the context of IVF and also in the context of embryogenesis. And I will present a new model that we constructed in this field. And I will end up with a model for transmission of COVID-19 in indoor spaces. So going to in vitro fertilization, as I have mentioned, this is the primary way of treatment for infertile couples around the world. And there are so many IVF clinics around currently. The field has progressed a lot, but not a lot in the mathematical modeling front. So we have a project going, funded one, with a clinic, UK-wide IVF clinic. And in this, we are looking at various challenges that have to do with mathematical modeling of IVF. So in collaboration with this clinic, we have looked at thermal modeling in embryos. I will explain that a bit later. The key, the holy grail in this field is how to choose the best embryo to transfer to the potential mother. And that's still, a very uncertain choice as is happening in clinical practice. And we're also in collaboration with our collaborator, Professor Kaswan in Cardiff, look into devising new algorithms for determining diffusion coefficients in fertilizing eggs, which has to do obviously with the early hours of fertilization before an embryo has formed. So I will show you some pictures. This is from our collaborators, the London Women's Clinic. This is a frozen embryo. So there is a lot of research on the fresh embryo transfer, but not a lot on the frozen embryo transfer. And this is increasingly important because more and more people, especially now with the pandemic actually, opt to freeze their embryos to then at a later point try to do the implantation. So the question is, can you understand the way this embryo behaves when it's get taken out of the freezer, and from those morphokinetic parameters to predict which one of the ones you have is gonna be the more successful to create pregnancy. And so, as I said, this is a thawing embryo growing. The pictures are every 10 minutes. This is from the incubator in the clinic. It's a funded grant with my collaborator at Cardiff, Dr. Thomas Woolley, and we also have a PhD student working on this, Tim Ostler, who I'm also going to mention later. So, for example, I cannot get into a lot of details because I opted for showing various projects. So one key question is how can we use this growth rate you have seen in the previous video to correlate with the pregnancy outcome? And of course, when a mathematician hears the word correlation, we translate to statistical correlation. So this is what we did precisely. We statistically analyzed the growth rate with the pregnancy rates that we were given by the clinic. We had only 58 embryos, and with the embryos we had, we found that the embryo's growth rate is not a predictor of pregnancy, as they had hoped it would be. But the 58 embryos point is important, because we establish with our statistics, the power of the statistical test, that actually to really be confident in our results, we need about 500 embryos. So, and that's very difficult to obtain. A primary reason now is the pandemic, and the project has been going on since October 2019, but the embryologists have to stop their busy work with helping the patients, and then have somebody at the computer looking at these incubator images. So this is one of the challenges of working with math biology problems that I'm sure many of you are already aware. And so we're waiting for more data. We eventually hope to have that, and then we're going to rerun the simulations. But we have already built the framework, and it just needs more data. So we asked 2 more questions, again using statistical testing. So is the embryo mean growth rate different between day 5 and day 6 freezing? So it's a very hotly debatable question in the IVF field, whether this embryo should be frozen on day 5 or day 6. The current practice in the UK and many other countries is that you freeze at day 5, but day 6 has been obviously considered. And we want to understand in this investigation about the growth rate whether there is an indifference between day 5 or day 6. We found statistically that there isn't. Again, there is this caveat that we need more embryos, in this case about 192. And then the other question we asked statistically is, are pregnancy rates affected by whether the embryo is frozen on day 5 or day 6? So this is a related question. So is it better to transfer in day 5 or in day 6 embryo? The answer is again no, but then here we need about 700 embryos, if I remember correctly, to believe our conclusion with confidence. As I said, the framework is there, it's just waiting for that data set. We also talk with other people, but of course, because we have this industrial collaboration funding this project, we cannot really be out there asking other people. It has to go through them somehow. And then we also looked at thermal modeling. So that's on a different scale. So we look at this embryo inside the so-called cryotop device. This is the embryo here. This is little tiny, it's a little sphere, the way we model it. We model this thing as a cylinder. There is liquid nitrogen inside and the air outside. There is a plate on which the embryo is sitting and the liquid around it. So we solved heat equation for this device in COMSOL multiphysics and compared to an analytical solution with good agreement. So this is the results of our simulation. As I said, we modeled that tip of the cryotop device. We found with dimensional analysis and thinking in a model always what is important and what is not important, that the embryo and the plate don't really play a role. So what we're really doing is modeling the temperature inside this cylinder with the liquid nitrogen. And we find that using these simulations, that the time taken to reach the devitrification, the unfreezing temperature, is 20 seconds. A bit more than 20 seconds. This is fine, actually confirms the clinical practice, because this step in practice happens in less than 20 seconds. Of course, there might be other complications, like that liquid nitrogen I mentioned is boiling. So it might create bubbles, it might, it's moving, so it might create some changes in the temperature field. So we haven't yet looked at that, and something we're planning to do with this PhD project, this fluids problem. We also looked between this close collaboration with the clinic, They said, we have these frequent review meetings with them. They said, oh, is the freezing rate varying with the number of X embryos? Can you simulate this in COMSOL and tell us whether adding 1 or 3 embryos on this plate really plays a difference in how quickly they are frozen? And we found that we modeled the worst case, that there is a minimal amount of cryoprotectant solution around the embryos. And basically we found that it really doesn't matter beyond 2 embryos. So the conclusion is vitrifying multiple embryos like they want to do in order to be more efficient does not affect vitrification rate. And this is an important prediction for them. We also asked, does embryo configuration matter? This is the poster that we just prepared for the Fertility 2021 conference that all the IVF clinics are participating annually. And basically you can see here 6 configurations that we looked at, and we found that it really doesn't matter much. The worst case is this bounding sphere situation. It has a higher volume of loading material and has many large number of embryos and oocytes. So we are also mentioning oocytes here because they are also interested in freezing eggs, not just embryos. So that's the other job an IVF clinic is doing. So configuration of the embryos does not matter either. That's very important for them to know. It's a new result, so that's why it's gone into this conference. They are excited about it. We're all happy, and we're waiting for that data. And this will take me now to the work we do with our experimental collaborator, and that's Professor Carl Swan, who is also involved in the other with the clinic work. So this is about the early hours of IVF, and Professor Swan has determined with collaborators in 2011 in this paper that there is a correlation between calcium waves and egg mechanics. And why is that important? Well, I'm going to talk a bit about calcium later and how important it is. So it's a very important marker of IVF success. This has been proven in the literature, again, very recently, 2016. But we cannot image calcium without destroying the fertilizing egg. So it's like no gift at all. But the correlation with mechanics, because we can image mechanics non-invasively, is very important, very useful, and it could potentially lead to non-invasive methods for choosing the best embryo early on, not at the stage that I was also talking about later with earlier with the clinic, but from the very first hours. This is again a very important thing to achieve. There has been a patent that our collaborator had done with Cambridge University, which is now lapsing because basically of lack of mathematical modeling progress on the problem. And this is a gap we are trying to fill with this collaboration. So again, you can see Thomas Woolley here, with whom I work on various projects. Carl Swan is a professor I mentioned, and we have this research student. And we have to start from somewhere, right? This is a very complicated problem because you have to understand how this material behaves, and which is the egg, fertilizing eggs. You have to understand this calcium spatiotemporal variations. And before I go to the next slide to show you the modeling approach we have chosen, I will play this video. And you can see what I mentioned about the correlation between the variation of calcium, which is the top panel, and the variation in the motions, the mechanical effects, the mechanical motions in this egg. So you can see that the correlation is pretty good up to here, and then there is something not as good here, and this is still not understood why this correlation breaks down, so to speak. A potential hypothesis is that it has to do with the fact that this egg is not a 2D object, it's essentially a big 3D sphere, big in comparison with other cell types. So we started this modeling approach, carrying on from a paper of 2018 by Carl and Thomas. And before explaining that, I will give you very briefly that calcium is a very important messenger of life and death. You can see this calcium toolkit, as it's called, in this Nature Reviews article by Berich. She was a very leader in calcium signaling in Cambridge. She sadly died recently. And this calcium is everywhere, so it's also in IVF, very important marker. And how can we model this? What's the modeling framework we want to achieve, we want to put forth? So we have to abstractify, as we also do with models. This is our egg. This is the cytosol of the egg. We model the endoplastic reticulum, which is a calcium pool with high concentration of calcium as another domain. And then this pool of calcium communicates with the cytosol through channels or through receptors. We call them the IP3 receptors, which are activated by both calcium and another chemical called the IP3, sorry. And there's also calcium that comes from the cytosol into the ER with a pump mechanism, because it's low concentration to high concentration. And this ultimately, in the deterministic realm, leads to this kind of PDE that has diffusion. It has the flux from the ER to the cytosol and so on. The pump flux and, sorry, another flux from the outside. In this case, we don't have flux from the outside, it's an isolated egg. And all models should capture the so-called calcium-induced calcium release from the endoplastic reticulum, abbreviated as ER. So the new model we started with is, after close guidance from the experimental collaborator, we reviewed the series of recent models on calcium signaling fertilizing eggs. And as it happens sometimes, nobody had incorporated an experimental data, experimental paper that gave more accurate information about how that gate on the endoplastic reticulum opens and closes with calcium and IP3. So this was summarized in this quite early experimental work. The reason that the experimentalist, Professor Swan, is saying this doesn't happen is because there were no mathematicians. It was like more biophysical, the approach. So we went more mathematical. We studied this curve, and then we incorporated it. This is a curve, and you can see the experimental data and the fitting that happened by the Mack and Foskett. And we incorporated this as a first step into understanding this complicated problem of calcium signaling fertilizing eggs to a model of two ONDs. We split the open probability into two parts, and these are the two ONDs. C is the calcium in the cytosol, and N is the percentage of receptors on the ER that are openable. So we have two variables. And we find oscillations that made the experimentalists happy. We have been looking for them for months, trying different kind of models. In the end, we did get these oscillations we were looking for. And they also have the right qualitative features, which is that the amplitude increases with IP3 and the frequency stays approximately constant. So the IP3 is this control parameter in this case, and it can increase. So this is low IP3, higher IP3. You can see how the blue, which is the cytosolic calcium, has increased, but that the frequency, which is the ups and downs, of course, I guess we all know this, is more or less constant. And this is fine, but then an important next step, again, driven by this close experimental collaboration, is that we have to respect the fact that IP3 is actually varying dynamically in these fertilizing eggs. This is a specific feature for this cell type and some other cell types. And also we have to eventually add in spatial structure of the ER, and we're going to continue this. We already started this with Thomas Woolley again, and another student, Luke Heirene at Cardiff. So I did mention calcium and mechanics in the context of early hours of IVF. Switching to a different scale now, I want to go more into multicellular problems, and in particular embryogenesis. This is some work we collaborated with experimentalists and with Professor Maney, that I have seen him here today, and other people. So what about these mechanics and calcium? So you have chemistry, biochemistry, you have mechanics, so the motions and the push and pulls that happens in the cells. And they have seen that, for example, in airway epithelial cells, when you poke the cell, you can get dramatic intercellular calcium waves. You can see them from the top panel to the bottom panel, how they evolve. Then they also looked at calcium waves in the skin, it's in keratinocytes, and that you can see more in that paper of 2014. Also in endothelial cells that are sheared by flow, they found that when this flow is shearing the endothelial cells, again, inside the cell, you get calcium waves. So that's from 2016. And then the motivation for the model I'm going to talk about came from a visit of Professor Chapman in Oxford back probably 20 years ago now, 15 years ago, to Caltech. He came back with some insight that these experimentalists in Caltech were working on growing frog embryos. And this is the next part of the frog embryo, and you can see these flashes. So you see this dramatic calcium wave, and also it's accompanied by motion. So this is coupling of calcium and mechanics. And there is also found that disrupting calcium inhibits the embryo's development. That's very important then. So as we said, calcium is a very important messenger. And in fact, it's been proven experimentally that if you disrupt this calcium choreography, your embryo is going to have problems, sometimes very severe. So that was from 2001, 19 years ago, sorry. And then very much more recently, there was another experimental group that they showed that the contractions in apical constriction, which is a fundamental process when in neurogenesis in embryos, the contractions there have to be preceded by calcium transients. And again, they have shown that if you disrupt these calcium transients, you lead to malformations like spina bifida. So you can find more information about the experiments in the 2015 paper. I'm going to play this video now. And you can see here a different kind of calcium signal. It's not intercellular anymore. It's what they call autonomous calcium flashes. So but the important thing is this is a multicellular problem, because all these cells, they have to coordinate in order to form the neural tube. So, so as I said before, the main finding from these experiments that calcium elevation precedes contractions in neurogenesis, in apical constriction. So this is a picture that shows this more clearly. It was in this paper with Professor Maney, the two experimentalists, and Professor Chapman that came out last year. We have reanalyzed some data from those experiments to show this effect more clearly. And we found that calcium oscillation frequency and amplitude, the amplitude increases as time goes by, and the frequency also increases. And here also you see the cell surface area. So what apical constriction, as the name says it, is constriction of the cells. Their area, their apical surface area is constricting and is becoming smaller and smaller in a pulsatile way, and hence the oscillatory features that we are studying here. And then we thought what would be a good model to capture the qualitative features of this behavior. There were some old mechanochemical models by Oster and Murray, both very well known in the mathematical biology field. And these models, even though they did use a viscoelastic model for the mechanics, for the cellular, for the embryonic tissue, they used outdated bistable kinetics. This is because they did the best they could at that time, because there was no experimental data to update those dynamics. They were subsequently found to be excitable, and I'll show with pictures what I mean. So we updated those models with excitable calcium dynamics, which are much closer to more recent experimental data. And there is a joint grant where Christodoulou and Skouridis in Cyprus, they do more experiments on the mechanics, and we do some modeling for them. But what is this new mechanochemical OND model? And basically it distills down to a set of 3 ONDs. The first equation is again for the cytosolic calcium, and then this calcium now is across the tissue, not inside one cell, so in different scale. You again have the active IP3 receptors, here called with an H rather than N that we had before. And then tissue dilatation is, it starts from the viscoelastic force balance equation for the medium, that the tissue is assumed to be viscoelastic material, Kelvin void viscoelastic material. But then we can show that this can be recast as this OND for the tissue dilatation. So there are 2 parameters here that are of interest. One parameter is mu, that tracks how this IP3, this very important chemical, is incrementally varied. And then you also have here a lambda, which is coupling this equation of mechanics to the cytosolic calcium. And you can see that it's a 2-way coupling. This is a new feature in our model, this 2-way coupling, that because you also have here calcium. So our interest is to vary these 2 bifurcation parameters, mu and lambda, and see what happens and whether we recapture the experiment's qualitative features. There is an important note to be made here, that there is a small parameter in front of the cytosolic calcium derivative, and this is to reflect the well-known fact that calcium is a very fast messenger. And this we can exploit later on for asymptotic purposes. For now, we just leave it, and we show the bifurcation diagram for this, the A3. This was a model from 1993 that didn't have mechanics, so it's the A3 and AL model. And this means that lambda parameter is 0. It's just a mu varying. So as this mu parameter is varying from left to right, you can see in this excitable system that I mentioned earlier that initially, for small IP3 levels, you don't have oscillations, you just have a stable steady state. Then you get a Hopf bifurcation here, which means that oscillations are generated. These oscillations amplitude increase with increasing IP3. You eventually lose them through another Hopf bifurcation, and you get again a stable steady state. So this is a quite generic bifurcation diagram that is also produced by many other calcium models, like the Lee-Riesel model, if somebody here works on calcium signaling. And then what happens, so I also have, I can show you the hallmark of excitable system is also this actual action potential that happens just before these non-linear oscillations, which are also called limit cycles, of course. And then the stable steady state, after you lost the stable oscillations, is a decaying oscillation, decaying to the steady state. So we varied the lambda then, we created a bifurcation diagram for mu. So this is the R3 case, and lambda, which is a new thing we have done. And we found that if we increase lambda a lot, but well, to a certain value, the coupling with mechanics increases. And for that, at some point, you lose the oscillations, the calcium oscillations, which are all inside this so-called Hopf curve. And it has been shown experimentally that this loss of oscillations is very important because it's exactly what leads to those embryo abnormalities I mentioned earlier. So it's very nice that we have, in this case, a semi-analytical way of tracking where these oscillations exist, as showing this feature that by varying the coupling with the mechanics, at some point you're gonna lose the oscillations. In experiments, they do this with some more forcing they apply. I don't exactly understand it, but our experimentalists understand it very well. So we had a lot of discussions what it means for the experiments. So we reconciled that this is exactly what happens in the experiments, that increased mechanical stimulation makes the calcium oscillations vanish, and this is bad. And just to take some new values and see what happens as lambda is evolving, you can see here that when mu is 0.25, so in the R3 model, you wouldn't have oscillations, it's before this oscillation regime. You start off without oscillations for a certain up to this lambda, then you have oscillations, then you lose oscillations. So in some sense, this diagram is quite similar to the one I have shown for the mu. But then if you start off with oscillations in the lambda equals 0 case, which is here, you see that you can see these oscillations. So this is the maximum amplitude, this is the lower amplitude of oscillations, and they eventually vanish. And basically, if you summarize these insights, you see that the frequency increases as lambda and mu increases, which agrees with experiments qualitatively. And then I mentioned that parameter epsilon. I'm not going to have time. Let me check the time. I'm not going to have much time to go into this in detail, but just to say that we have this small parameter. So as mathematical modelers and mathematicians, we think what we can do with this. How can we use it to understand our model analytically? So we consider asymptotic methods when epsilon tends to 0, and you have the case of one fast variable and one slow variable. You can find these results in a preprint in the archive with Professor Maney and Professor Chapman. They were the co-authors. And the important thing here, mathematically more interesting than biologically, is that whereas the well-known van der Pol oscillations, they look like this with this cubic that many of you have done in your undergraduate modules of third, second year, you see here that you have this slow ascent, fast movement, slow back, and then you go back to the same point. But here you have a slow ascent, it has a rapid excursion, and because the null line is not a cubic anymore, have the last excursion, and then it goes back without the second phase of slow descent. So these are novel asymptotics, and it's a fast slow dynamical system with one slow region and a so-called transition layer. So, and we can extend this understanding to looking at the mechanochemical model asymptotics. So again, epsilon here is small. So you have one fast variable, which is calcium, and you have two slow variables, which is the number of openable IP3 receptors. And then, as I said before, theta is a tissue dilatation. And there you can see in the preprint more results about this case. I want to move on now to a spatial problem. So it's the same R3 model, but then you add diffusion, which is very important actually. I mean, our initial assumptions were, okay, we're gonna forget about diffusion to understand the system dynamics, but diffusion plays a huge role for calcium. So we add this diffusion into the R3 model, which was there in the original paper actually. We just studied it in more detail, so this is not new. I remind you again what was the bifurcation diagram without diffusion, and then I will show you the simulations with diffusion. So, for example, the mu 0.25 case, the own bifurcation diagram was predicting that you have a stable steady state. So you put a little Gaussian here to excite the medium, you find that the Gaussian decays very shortly after. So it's the same behavior qualitatively even within diffusion in. Then what about increasing mu to 0.288? So this is a corresponding, it's a solitary wave, as you can see, it's traveling with a certain speed. And it's, the equivalent of the action potential in this spatially extended system. Then you increase more to 0.3 for mu, this tracking the IP3 level and going up and up. And you find the so-called periodic wave train. So it's the equivalent to these limit cycles or nonlinear oscillations. And what do you expect when you increase mu more from the owned bifurcation diagram? That these oscillations should die out. Do they? Yes, they do. So we get these dying oscillations. So the spatially extended system ties up with the insights we got from the owned bifurcation diagram. And as I said, solitary waves become periodic wave train and then decay. And coupling with mechanics, it's again interesting. So this is new then and now. So we do have the diffusion in, and then we put this equation for tissue dilatation. And we take, for example, the case of mu 0.28, where the R3 model does not have oscillations, but does have a solitary wave like this one. And what happens when lambda increases from 0 to 0.1? Well, you go into this region. So this diagram that came from linear theory predicts that you're going to have oscillatory instability. So in nonlinear simulations, this is a periodic wave train as predicted. And then increasing lambda even more, you still get a periodic wave train with a slightly different frequency, but then eventually you have exceeded this point. So you are at around here, and the Hopf curve diagram predicts that the oscillations will die out, and indeed they do. So this is a proof of concept to a spatially extended system on this our approach of mechanochemical modeling for embryogenesis. So then you can see the same R3 model in 2 dimensions, no mechanics. And you can see again that these insights you got from the OND model carry out to this other spatial problem where now I don't have 1 dimension, but I have a radial symmetry. And this is work we are doing with Abhishek Chakraborty, who's a PhD student in Cardiff with me, and another colleague who is currently in Monash University in Australia. So basically, Ricardo is a FEM expert, and he's been adding in FEM, we constructed together in collaboration with this experimental input, a FEM model, mechanochemical FEM model that can accurately model the experiments of the experimenters. This is in evolution, so I'm not going to show anything more about this. But you can still here see this fascinating. We really like to see these waves, so perhaps I'm a bit carried away to show this. And I will finish in the last few minutes, just less than 5 minutes, about our recent COVID-19 modeling. And this is about modeling airborne transmission in indoor spaces. So this is a very obviously critical problem, as the pandemic's unfortunately second wave is evolving. We got a grant from the Welsh government that is gonna employ 3 PDRAs. One of them is already, one postdoc is already in place, and we're gonna get 2 more with the new year. And it's a collaboration with the University of Oxford and another company, Smart Separations Limited, who are doing antiviral coatings. So the idea is that we are interested in this. We're interested in small droplets that travel as a cloud through the air, because the large droplets that travel ballistically through the air, they are the ones that land more or less within 2 meters from the person that has produced them. And this is what motivates the social distancing of 2 meters, right? But it's been a recent, relatively recent event, because it's since July that many scientists have been saying that these small droplets could also play a role in transmission. They call it the aerosol transmission, because these droplets are not bogged down by gravity. And as I said, they travel as a cloud, and they can go much further in the room, so they can increase the number of infections, even though we keep the social distancing. And there was updated guidance by the Center of Disease Prevention and Control in October, acknowledging airborne transmission as a potential route of transmission in poorly ventilated spaces. So ventilation is very important in this, and this is what we set out to study. We looked at the classroom for obvious reasons, because educational institutions around the world are very interested in how to optimally operate their spaces and keep infections to their students and staff to a minimum. So we look at the case of one infectious person in the middle of a square room. We have air conditioning unit that generates this uniform airflow taken from data that have to do with air conditioning. And we also have an air vent that takes air out. And we looked at 4 ventilation settings, very little, very poor ventilation, poor. Then there is one recommended before the pandemic by the Association of Heating and Refrigeration Engineers, ASHRAE Society. And then they also recommended ventilation for when the pandemic started, that of course is better than before. So we did these 2 recommendations by this, the society giving these guidelines. And we also looked at poorly ventilated spaces, motivated again by other studies in classrooms and other data available. And we looked at, as I said, one infectious person, and how does this person behave? We didn't look at coughing and sneezing up to now, looked at breathing or talking with or without a mask. So it's a variety of scenarios, as you can see here with all these choices. The advection, we use the framework of an advection diffusion model. So basically we model this person breathing or talking as a source of the viral particles, and we model the ventilation as a global sink. We also model here the advection, and it's very important here to note that, because one obvious question is, what do you do about the turbulent flow in the room? We use here, instead of the Brownian diffusion coefficient, the Edding diffusion coefficient, which is an average way to take into account turbulence. The reason we did that is because we wanted to steer away from the more complicated CFD models, and we wanted to be more complex than the other very well-used models, which are called the well-mixed room models, or like the Wells-Riley models. For people that are working on this, they would definitely know these models. So you have these 2 models, the Wells-Riley models and the CFD. We're somewhere in the middle. We can get an analytical solution for this equation based on the method of images. We have implemented this, and our key outcome is some time to infection maps. We informed from experiments, anything that exists out there, we thoroughly scanned the literature to understand how many particles does it take for a person to be infected. And you use this as the infectious dose. We found that this is about 100 particles. There is a breathing rate that we took from the literature. This is well-known parameter. And we have produced some recommendations. I'll give you just one example for the interest of time, that the ASHRAE Society I mentioned of refrigeration and heating engineers, if we adopt that, the best ventilation out there, which is difficult, of course, to achieve in many places, you would allow in a classroom or the one we modeled, 37-minute lessons followed by 35-minute breaks. But if ventilation is poor, 25-minute lessons are allowed if followed by 166-minute breaks. So we can see here that if ventilation quality decreases, this can dramatically change the recommendation for how much time you can safely stay in the room before getting infected. So I talked about the time to infection maps. So they look something like this. For example, this in increasing ventilation quality. So you can see here the best ventilation, the before pandemic recommended ventilation, very poor and poor. So you can see here, for example, 20 minutes became 35 minutes, 100 minutes, 175. So the time to get infected increases, obviously, as the ventilation quality increases. And we just submitted this this week to a journal with the title Modeling Airborne Transmission of COVID-19 in Indoor Spaces using our advection diffusion reaction equations, and this is with my collaborators, Professor Ian Griffiths in Oxford and an MSc student we had in Cardiff, Zeharia Lau. And just to give the overall summary, and I have to finish, I talked about IVF, calcium signaling, calcium and mechanics, some asymptotic analysis, added diffusion, and then I briefly looked at a new model for COVID-19 transmission in indoor spaces. And I would definitely have to acknowledge gratefully all my collaborators from industry and experimentalists for all the nice projects and ideas that we have been working together. So thanks a lot for your time, and yeah, thanks a lot.
So thank you, Dr. Katrina. And it was a wonderful talk. And for questioning and discussion, your ideas, thoughts, comments, I will hand it to Dr. Humayun Kabir, and he will conduct the session and conclude the session as well. Thank you very much. Dr. Humayun,
thank you. Thank you very much, Professor Dr. Pavel Shariar. So I have received a couple of questions, but before that, I'd like to thank Dr. Katrina for her wonderful talk. So I have received a question from Mr. Dipesh Bormon. What is the biological significance of various kinds of bifurcations, like Hope bifurcations, saddle node bifurcations, and so on, in system dynamics? Biological significance.
Yes, please carry on.
Yes, what is the biological significance of different types of bifurcations in system dynamics?
Yeah. So, so the Hope bifurcation I talked about, right? So it's when you don't have oscillations, you can get oscillations. That's the most important one in calcium signaling, because what you see everywhere is these calcium oscillations. There is another bifurcation that is the saddle node one, that is about bistability. And this biologically would mean that you have two possible steady states. So the model that I have shown has a very thin region of bistability, and hence I didn't elaborate on that. But yes, in a more general, as a more general comment, you really have to track Hopf bifurcations in many systems that you know from experiments have oscillations. And also you have to be mindful of bistability regions.
Okay, thank you. He has one supplementary question.
Yes.
How can we relate periodic oscillations in real life problem? How can we relate periodic oscillations in real life problem?
For example, the way that it would work, like for example, I would take the calcium signaling in IVF that we have been working with Professor Carl Swan. He knows, and also many other people before him, that there are these dramatic oscillations of calcium in the egg when it's undergoing fertilization. So you already know that there is a physical, there is an oscillation out there in the experiments, and you want to use the model to understand how that is generated. So this is a connection. As modelers, we try to understand the things that we have observed in reality, in experiments or in societal problems. For example, you would observe how society rules are and stuff like that. So it's at the heart of modeling. Am I answering the question or?
Yes, I think it is
Yes.
okay. Thank you. So I have a question. So in the 2D simulation, you have shown a radial symmetric case in 2D
Yes.
simulation. So in your simulation, did you check the parameter values from the bifurcation diagram where you have oscillation in 1D? So is there any impact on 2D of that oscillation? Or
A very good question. We were wondering also about this, and basically how does going from 1D to radial changes things? Well, it seems that it doesn't, and because I think something I didn't emphasize perhaps earlier is the diffusion value is small, right? So it's a small perturbation in a sense to the dynamics, even though it is important and it has to be there to generate these waves. So you don't find much difference between these transitions, whether you are in OND or 1D spatial or radial spatial. I think that's the question, right?
Okay.
Yeah.
Okay.
So it's at the moment it's all tying up, but I think somebody could be looking at the analytics of this in more detail to see if there are some corrections to the mu value that you get oscillations at due to the diffusion.
I see. Okay, thank you. So we have a few minutes. So from the audience, we can receive one or two quick questions if you have.
I have a question, Dr.
Yes, please, Professor Dr. Usman Goni, please ask your question.
You show us Hopf bifurcation in 1D case, and the limit cycle solution become unstable first, then it becomes again stable by another Hopf bifurcation.
Yes.
So my question is, how did you calculate the stability of your limit cycle solution?
So for example, this one is with XPPOT, it's a continuation software that is based on Otto. Some other people use, yes, so it's Otto, basically it's Otto encapsulated into this GUI that Professor Bart Ermertraut has done in Pittsburgh. He has also a science book on this, so that is very nicely written. The software itself is kind of tedious sometimes. So other people would use, for example, MatCont, which is something you can run through MATLAB.
Yes.
So these are the bifurcation tools that somebody could use to generate a diagram like this. And in terms of the transitions, we also did linear stability analysis to get the, where you can get from stable spiral to unstable spiral. But I think you are asking about the non-linear bifurcation diagram, right? Not the linear stability prediction.
Dr. Usman Goni is.
Yes.
Yeah.
So my next supplementary question will be, is there any impact of this 1D Hopf bifurcation in the 2D numerical simulation? Did you find any irregularities in your 2D simulation?
Not
we
yet.
found
for this 1D hop bifurcation?
yes, we found some additional bifurcations that are very interesting. And at the moment, we don't know how to explain. I didn't put these pictures in, but they are in all summarized nicely in an MPhil thesis of Abhishek Chakraborty that was finished in October. And if you drop me an email, I can send that thesis to you, and you can see these additional bifurcations you get in space due to the spatial effects. So you do get these transitions, but then when you increase the mu inside the oscillatory regime, you get periodic wave trains. Yes, this is the prediction, but then these periodic wave trains change their features also. So there are some secondary changes there that you get only with the spatial extension.
I see. Okay, thank you.
Okay.
Yeah.
Thank
Okay.
you
Next, Dr. Kamruzzaman, you have a question. Please ask your question, Dr. Kamruzzaman.
I have a question. I have a question about airborne transmission in COVID-19.
Yeah.
So that's actually about a narrow corridor, right? So this is one of the latest invention of COVID-19 and the serious risks for the population. So actually, what type of population are in the serious risks for that type of narrow corridor or airborne transmission? In which area? Because there are different types of like school, hospital. So what type of populations are in major risks about this airborne transmission in narrow corridor?
So what we studied here is for a classroom. We just
about the classroom, yeah. Mm-hmm.
Yes. So, and this we assume that nobody has visible symptoms. So it's so it validates our assumption that these are people that are symptomatic, that are breathing or talking, but maybe they carry the virus. In a hospital, there has been sampling data paper just came out a couple of months ago, but I haven't seen modeling. I've seen modeling in restaurants, for example, and poor ventilation. This Guangzhou restaurant in China. So it really depends on the setting. So for us, what we looked is breathing or talking in a classroom. You can extend this idea as long as you assume that there is no visible symptoms like coughing or sneezing to any other location. A hospital would be hard to perhaps do that because in hospitals people go when they are sick. But let's say a supermarket or one, for example, our IVF clinic collaborators are interested because there you have to be healthy to go and do the IVF. So it's places where people carry out their activities, but they don't have symptoms. So the classroom was just a case study. If I understood the question, because I didn't hear everything, unfortunately, so I'm just answering approximately, perhaps.
Yes, so I have one supplementary question actually about COVID-19,
Yeah.
about the reinfection. So have you any idea about what about the reinfection? How many populations can be reinfected, or about the current availability of data? Reinfection of COVID-19 risk, yeah.
Yes, yes. Okay, so basically now I understand better. Sorry, also your previous question, because as I said, I didn't hear all the words before. If it's about population dynamics models, so this is in different scale, right? So this is inside the room. But there have been people that, there are many models actually, that have been looking at the epidemiological side and different types of populations. You have the compartment models, CEIR models are usual choice. And people in that context of the 4 ODs of susceptible, exposed, infected, and recovered, they have been also extending that and also adding reinfection in some cases. So I'm sure that I haven't been following in the last month because we concentrated on this room scale in our models, but I'm pretty sure there are papers out there doing that kind of reinfection rate, reinfection risk, and seeing how it affects epidemiological parameters.
Okay, thank you. So,
Yeah.
Okay, thank you very much. Let's stop here due to the time constraint. Okay, so may I request Dr. Katrina, could you please stop your slide sharing?
Of course, yes. Thank you very much for the invitation again. Bye.
Okay. So we have a small appreciation from our society. So this is a small appreciation on behalf of Bangladesh Society for Mathematical Biology to Dr. Katrina Cowrie. And we will send it to Dr. Katrina Cowrie soon.
Thank you very much.
Okay.
Thanks.
And once again, I'd like to thank Dr. Katrina Cowrie for accepting our invitation and for your wonderful talk. And maybe see you soon anywhere of the world. Last year we met in Oxford in the celebration of Philip's birthday, and hope to see you again. So thank you very much.
I also look forward to that. Thank you again. Bye.
Thank you again. Bye. Okay, ladies and gentlemen, now we would like to move to our next session, the second scientific session today. So the speaker is Professor Dr. Youngjung Kim from Korea Advanced Institute of Science and Technology, South Korea. So first of all, I would like to extend my sincere thanks on my personal behalf and on behalf of the society to Professor Dr. Youngjung Kim for accepting our invitation and give his kind consent to give a talk in this international e-conference. So I met several times with Professor Dr. Youngjung Kim in Japan, in Korea, in Taiwan also. Maybe 3 years back, I was invited by Professor Kim in National Institute of Mathematical Sciences, South Korea. So that was really a wonderful workshop organized by Professor Kim. So once again, I'd like to thanks to him for joining with us. So this session is chaired by Dr. Mohammad Kamruzzaman from the University of Dhaka, Bangladesh. Dr. Mohammad Kamruzzaman is also serving as the Joint Secretary of Bangladesh Society for Mathematical Biology. Now, I'd like to request Dr. Mohammad Kamruzzaman to conduct this session. Now, over to Dr. Mohammad Kamruzzaman.
Thank you, Dr. Humayun Kobi. So, dear participants, ladies and gentlemen, good morning, good afternoon, and assalamu alaikum. Welcome to the International Conference on Recent Advances in Biomathematics, organized by Bangladesh Society for Mathematical Biology. In this second session, our keynote speaker is Professor Dr. Youngjung Kim. Before starting this session, I want to use something about Professor Dr. Kim. Actually, unfortunately, my research has many similarities with Professor Kim, and in my PhD research actually is connected with the heterogeneous environment diffusion model in Bash and chemotaxis as well. So initially, I want to introduce Professor Dr. Kim. Dr. Youngjung Kim is currently a professor at the Department of Mathematical Sciences, Korea Advanced Institute of Science and Technology. He achieved his PhD in mathematics from University of Wisconsin. Professor Kim is also a professor at National Institute of Mathematical Sciences, South Korea. He was a visiting assistant professor at Department of Mathematics of University of California at Riverside. His research interests include reaction diffusion equations, dispersal in biology, chemotaxis, heterogeneous random walk, pattern formation, singular limits, discontinuous diffusion, and discontinuous reaction. Professor Kim is the chief of the partial differential equations lab of Department of Mathematical Sciences in his own institutes. Professor Kim is serving in the editorial boards of Mathematical Medicine and Biology, Mathematical Bioscience and Engineering, and Mathematics in Science and Industry. Professor Kim has given many invited and keynote lectures all over the world. He has also published a good number of very well-received expository papers and monographs related to different biological phenomena. So dear scholars, I believe you will enjoy this session. So now I would like to invite Professor Kim to present his valuable speech for the audience. Over there, Professor Dr. Kim. Professor Dr. Kim.
Yep.
Yeah, so please start your session, start your speech.
Okay, thank you very much. I'm very happy to be invited in this wonderful workshop. And okay, so let's start. Is my voice okay?
Yes, yes, it is okay.
Okay, now I'm going to make this one full screen. Is this okay?
Yes, it is all right.
Okay, then let's start. So this talk is about the heterogeneous diffusion. And then if the environment is heterogeneous, then it's natural to consider diffusion with the heterogeneity. Then this talk is just about what should be the correct diffusion equation in such environment, and then how to apply, if we apply this heterogeneous diffusion model to biological invasion or some chemotaxis model, then what can you get from this new diffusion model? So that is basically the story of this. And the focus of this talk is on the application of this diffusion model to biological invasion models and then chemotaxis models. So I'm not going to try hard to derive this diffusion model. So that is a different story. So I'm going to skip that part. Wait a second. Okay. So before talking about the diffusion, you probably know what is the heat conduction. So if you heat the rod at that one place, then heat transfer from hot place to low place. Then the Furier's law of heat conduction says that, heat flux Q is given by gradient of temperature T with minus sign and the conductivity K. And this conductivity is property of material. So if you have different material, then you have a different conductivity. For the homogeneous conductivity, this means if the material is homogeneous and this conductivity K is constant, then what should be the heat equation? Then here is U. U is heat or heat energy and minus divergence of flux. If we take this, then you get this equation. If K is constant, then K comes out, and then you get this equation. Now, what is the heterogeneous case? So heterogeneous case, if K is not constant, then you have to stop at this place, and this is the correct heat conduction equation. So this is heat conduction. Now we talk about particle diffusion. What is particle diffusion? If you put some particle in the water, then eventually it goes to equilibrium, which is a homogeneous state. Then what is Fick's law? Fick's law is that Fick's diffusion, so diffusion flux is given by this relation, which is a mimicking of heat flux. So if diffusivity D, so this D is called the diffusivity. So homogeneous case means this diffusivity D is constant. Then what is the diffusion equation? Then it's U is the chemical density, and then this is minus divergence of the flux. And since D is constant, this comes out, and you get this term. So this is a homogeneous diffusion equation. Now, what happens if D is not constant? Now, there are big difference between conductivity and diffusivity. Conductivity K is more or less the property of the material. However, diffusivity D is not the property of the material, for example, not the property of the water, but it depends on many things. For example, if the temperature changes, diffusivity changes. So if diffusivity D is not constant, what should be the diffusion equation? So if you believe this fixed law, then okay, you have to stop here. So this D cannot come out. So should stay inside if D is a function of X. Then the question is this the correct diffusion equation? And then, oh no. If diffusivity, in a heterogeneous case, I want to say the heat conduction and particle diffusion, they are completely different story, and this fixed law cannot explain the phenomena. So that is the point. And actually, that kind of thing has been known very long time, even if many people still use the fixed law. What is that? Thermal diffusion. Sometimes people call it Zola effect. What is Zola effect? So inside here, temperature is not constant. So in this place, temperature is hot. In this place, temperature is low. Then there is some temperature gradient. Then particle density never goes to constant. It gives you some heterogeneity. So this is kind of a long list of different phenomena. And certain things going to the hot place, certain things going to the low place. So fixed law cannot explain this. So to explain this kind of thing, what people do is, some particle is very sensitive to the temperature gradient and has a big diffusivity. Or some particle is less sensitive to the temperature gradient, and then, okay, they put the smaller coefficient. And they consider flux is given by this term, diffusivity, and here the conductivity. So this one is the way people do in the thermal diffusion. However, Chapman, this is the famous guy, Sidney Chapman, an expert in the kinetic theory. So he tried to explain this thermal diffusion without this phenomenological explanation. He thought that diffusion theory can explain this thermal diffusion phenomena. So he derived this diffusion law using a kinetic equation, and he derived, diffusivity D should go inside. And if this diffusivity D is not constant, then after applying the product rule, you will get this term, and this term will explain this thermal diffusion part. So this is the Chapman's law. However, before Chapman, Wallride, he considered the same situation, and he also tried to explain this thermal diffusion using diffusion theory only, and then somehow he derived this equation. And if you rewrite this one still has this advection term. So probably this advection term may replace this heat conduction term. So that one was the theory. And also this Chapman's law. This Chapman's law is also related to the Ito integral. And this Wallride's law is related to the Stratonovich integral. But okay, so let's skip. In summary, the heterogeneous diffusion models, there could be many of them. So if diffusivity D is not constant, then some people, I still find that some people use this diffusion law when D is not constant. But fixed law is this, Wallride's law is this is Chapman's law. And more generally, okay, you may also consider this kind of diffusion law. But somehow, all of them equivalent if diffusivity D is constant. But if diffusivity D is not constant, they are all different. Then what is the correct one? And then somehow I want to claim that, oh, all of these laws, diffusion laws, based on a belief that diffusion can be explained by the diffusivity only, even in a heterogeneous case. And I want to say that, no, we need more information. Something like it. And this kind of thing could be is the correct diffusion equation. And so here, what is mu? Mu is turning frequency. So we need something else. Sometimes if you use the departing probability, then okay, this gamma is the departing probability. Then if gamma is not 1, then this is the correct diffusion equation. Somehow I want to claim this kind of thing. But this talk is not about the derivation of this diffusion law. Okay. And this diffusion law looks quite complicated. But sometimes we want to simplify this one. And for example, if mu and d, this one is just 1, then we may obtain this diffusion equation. And this gamma is departing probability. And this diffusion equation is actually well known. And people call this one Fokker-Planck type diffusion equation. Or this diffusion equation also appears in the book of Okubo and Levin. Okay. Now, some other situations. If you consider diffusivity d and others just put constant, then this diffusion equation turn into this Waray's diffusion law. So somehow this kind of diffusion law is the one I want to use, and I want to show you that if you use this kind of diffusion law, then you can get some interesting phenomena correctly. So that is what I wanted to show you in this talk. Okay, so first, if we apply this kind of diffusion law to the ecological invasion problem, then we will get some better result. So that is the point of the first example. Okay, so this story is a story which is known quite well for a long time. Okay. So population growth in a heterogeneous environment. So okay, logistic single species model, this model is quite understood quite well. So here we use R is the growth rate, and U is the population density of a species. So we consider this one single species case. If you consider, and then this is initial condition, and this one is zero flux boundary condition. Then we know that there exists some steady state such that as time goes infinity, the population density converges to this steady state. So this one is well known. So this steady state will depend on this R, growth rate, and this diffusivity, D. Okay. The next one is more interesting. So this example is the reason I believe, I think heterogeneous diffusion should be used. What is this? This is a local Volterra competition model. So there are two species, U and V. And we have the same R here. And this is basically here, U and V, they are equivalent. The difference between these two species is that they have a different diffusivity D1 and D2. And the initial and boundary conditions are, okay, this is initial condition, non-negative, and no Neumann boundary condition on the boundary. Now suppose diffusivity are different and D2 is bigger than D1. That means V is a faster diffuser and U is a slower diffuser. And if we compete, then the result of the competition is quite surprising. The competition system 1 with 2 has 2 critical points where this one is stable and this one is unstable. So what that means? That means if you have initial, whatever the initial value is, the solution always converges to the stable one. So that means U becomes theta D1 and V becomes 0. That means faster diffuser V goes extinction and the slower diffuser U prevails. So this is the result of this one. And somehow this result, what is the next one? Okay, so this is the picture, or this is numerical simulation. And in this case, diffusivity is given here, and R of X is given here, and the domain is 0, 1. Now, initial value is given at some point. Then the population grows. And the faster diffuser has a faster diffusion, so they grow faster, and slower diffuser grows slower. So in the first stage, this diffusion helps. But in a different time scale, eventually faster diffuser goes to 0, and the slower diffuser take all. Okay, so the theory is correct. So the previous theorem here, this theorem is correct. And then as you can see, the solution eventually converges to a state that faster diffuser goes extinction, slower diffuser prevails. When I think about this result, I thought this one is a kind of a paradox, because dispersal is something essential for survival. But the result, but the previous theory says that dispersal, if you have dispersal, bigger dispersal, then you go to extinction. That means in the evolutionary, dispersal disappears. So definitely, this is a kind of a paradox. And somehow this paradox tell me that heterogeneous diffusion should be used to understand the role of dispersal correctly in ecological invasion problems. Okay. But actually, even a long time ago, people already considered the situation that dispersal is not constant. So here, this we call this SKT model, Shigesada, Kawasaki, Teramoto, in 1986, so quite a long time ago. So even that time, people considered the case that diffusivity D is non-constant. So what they considered is this kind of situation. They considered periodic environment. So one period is from 0 to here, and the same part repeat periodically. Now, this interval is divided into 2 patches. And the first patch, we call it good patch. Second patch, bad patch. Why this one is good? So growth rate R is 1. So population grow with rate 1 in this region. Now here, bad patch, because this growth rate is negative. So if you stay in this patch, population is decaying. So that's a very bad patch. Now diffusivity in good patch is fixed by 1. Diffusivity D in a bad patch is fixed with is not fixed. So bad patch diffusivity is dB. Okay. Now here, length or size of bad patch is 1, and the length of good patch is LB. So here there are 3 parameters: RB, DB, LB, and we fix all others by just 1. Now SKT model. So they considered this situation with a fixed law. And in the beginning, I told you that fixed law is something wrong. Still, many people believe fixed law is the correct diffusion law for this kind of situation. But I'm thinking, oh, no. That is not correct. So instead of this, what we do is, use this override law. So in the previously, where is the diffusion law? Here. So this one is the diffusion equation I want. Now, when mu and gamma, they are 1, we return to the Walray's law, and we took this diffusion law. Okay, here. And we do the analysis. And what is our conclusion? The conclusion comes here. Now, this is the invasion parameter regimes. So we have 2 parameters, RB and LB. Now, if we choose these 2 parameters, then extinction or invasion is decided. And this one is the invasion regime. This part is extinction regime. Now, here is a diffusivity. Now, what is the good situation? The invasion regime, if you are in this invasion regime, that is a good situation. Is it okay?
Yes, it is okay. Please carry on.
Okay.
Oh, sorry.
So this is invasion regime. Now, somehow you can see that if you change the diffusivity, this invasion regime changes. Now, if you decrease this diffusivity in a bad region, invasion regime increases. That means, if this result says that in a bad region, in a bad patch, if you decrease dispersal rate, then your survival possibility increases. Okay, so the conclusion of their paper is that, you should decrease your dispersal rate in a bad region. Okay, so this is the conclusion, but this one is quite counterintuitive. If you are placed in a bad place, then probably you want to increase your dispersal rate to move out of it. But this theory says that, no, you have to decrease your dispersal rate in a bad region. So, okay. Now, if you Walray's diffusion law, then actually you will get completely different result. As you can see here, if you increase your dispersal rate in a bad region, then invasion region or survival region increases. So if you use this model, then you have a completely opposite result that, in a bad region, you should increase your disposal rate. Okay, so the analysis of SKT model, their paper correct, but their diffusion equation, their diffusion model does not explain the situation. So the diffusion model is not correct. So that's why they have a counterintuitive result. So this is one example that choosing the correct diffusion equation is very important. And the wrong diffusion equation may give you wrong conclusion. And then, okay. So one of the model I have considered is this starvation-driven diffusion. So somehow we may consider starvation measure, like the ratio of this. So if this ratio is large, that means you're starving. Why? This U is a population. So if there are more population and more population, then more competition, then you probably starve. Now M is growth rate or carrying capacity. So if M becomes large, then U becomes less starving. So this ratio somehow show you how the degree of starvation. So this gamma should be an increasing function. And then use this kind of gamma and apply this one in the diffusion. And you may consider competition system. Then this kind of diffusion, this kind of competition system is the diffusion system, competition system with the disposal, heterogeneous disposal rate. So in this case, what I'm using here is the departing probability, not the diffusivity. So we considered this one, and we have some related papers. And here, in this paper, the authors consider the predator-prey interaction system. So they probably have a different reaction part. And also they considered intra-guild predation model. And then this one, this equation is what evolution of dispersal with the starvation measure with the and coexistence. And so these models, these papers are somehow papers that developing this kind of diffusion, heterogeneous diffusion model, and then had some analysis. Okay, so this part is some part related to the ecological invasion. Now, the next part is application of this kind of diffusion model to the chemotaxis theory. And chemotaxis theory is the theory that still a lot of people, a lot of mathematicians do the research and produce very interesting results. I'm going to briefly introduce you what is the chemotaxis. So when people do the chemotaxis theory, basically mathematicians do two typical models. The one model is about the aggregation. So this part is aggregation model. What is aggregation? So this is a typical example. It's amoeba. So if starvation starts, so here, okay, let's start from this stage. So here is amoeba. They eat bacteria, but after they consume all the bacteria, starvation starts. If starvation starts, then they produce some signal and they get aggregation like this, and then make some kind of a hump. And then somehow they crawl, and eventually they produce this stalk shape. And then at the top, they have spores. If they have the spores, then okay, then if a bug goes by, passes by, then they stick to the bugs and then fallen far away and they start again. So this one is the first kind of chemotaxis model. And second one is traveling wave phenomena. This traveling wave phenomena is, okay, there is a resource. Then bacteria, they consume the resource and they travel from, for example, start from center and then they go out. Or in a tube, you have a resource here. Then bacteria start from here and then they produce this kind of pulse and then move toward the food. So one is the traveling wave phenomena, one is the aggregation phenomena. And Keller and Siegel, they studied this, developed their model. And their first seminal paper, 1970, they considered this aggregation. Now in the third paper, next year, 1971, they considered the traveling wave phenomena. So they considered both cases. And the Keller and Siegel, okay, so they developed chemotaxis model, and this one now called the Keller-Siegel system, and a lot of people working on this one. And one of the basic assumptions of the model is that microscopic scale biological organisms, such as bacteria or amoeba, they can sense the gradient of a chemical and move toward or against the gradient. So this one is basic theory. Okay. So in their first paper, 1970, what they introduced is this chemotaxis model. So here, so A is the density of amoeba or addictive, and equation for this cell density is the first one. Now, this amoeba, when they get aggregate, they produce some chemical called acracin, and rho is the density of the acracin. And then here, this one is diffusion. Now this one is the production. This one is the production by amoeba, and this one is the degradation. Okay, so they consider these two systems. Now this one is the diffusion. Now this one is the advection. And this advection part, somehow they assume that amoeba sense gradient of this acracin, and D1 is the diffusivity. And this diffusivity D1 is given by this ratio. So basically this equation is, this model is a logarithmic model, not the minimal model, the logarithmic chemotaxis model. So this is their first paper. And after this one, so basically this model is just taking the diffusion advection equation. But in the next year, in the second year, they introduced model for chemotaxis. So they derived this equation using some random walk idea. And then they, introduced this new model. So this is actually obtained from the modeling process. But the first one is just taking the advection diffusion equation. Now in this model, this B is bacteria density. Now this is C is the resource or food. Okay, so this is the second paper, and then use this one to explain the traveling wave phenomena of chemotactic bacteria. So basically this is the equation. Now if you can see, as this B is the bacteria, and this bacteria, where is this? This one is the diffusion of the bacteria. And this S, gradient of that. So this one is the sensing the gradient. Now chemosensitivity, this one is given like this. So basically this one is V over S times the constant gamma. So this one is still logarithmic model. Many people are somehow confused that Keller-Segal model is minimal model. No, they never considered the minimal model. They always considered logarithmic model. Now this S is the equation for the resource. So this one is the consumption, linear consumption. So this one is the diffusion. But when they do the analysis, they deleted this diffusivity. Okay, so this is their model. Now, Keller and Segal, they said that microscopic scale bacteria sense the macroscopic scale gradient in an erratic way. However, amazingly, they show macroscopic scale chemotaxis phenomena exactly in an averaged sense. So they say, oh, it's quite amazing. Even if the bacteria, they are microscopic scale, but they somehow sense macroscopic scale chemical gradient in an erratic way, but they can show the chemotaxis phenomena exactly. Okay, that's what they say. But here I want to say that, oh, even if they don't sense the chemical gradient, they can show the chemotaxis phenomena exactly. That's actually what I wanted to show. And the theory I am developing is this second case. We can develop chemotaxis model using this new heterogeneous diffusion model without assuming sensing the gradient. Okay. So traveling wave phenomena. Somehow we consider it for the traveling wave phenomena. So traveling wave phenomena is about consuming resource. So aggregation phenomena and traveling wave phenomena, they are completely different. So we consider starvation measure here. Now it's a gamma is a departing probability. This one is an increasing function. So H is high, L is low. So definitely H is bigger than low. So the model equation is here. So now here what we do is, oh, we only have this diffusion. But even if you have this diffusion, if you rewrite this one automatically gives you this advection term. And this advection term is just enough to give you traveling wave phenomena. And M is exactly same equation of the Keller-Segal. So we consider this kind of system. And we have some related papers. And this equation, this model, this one is to derive this diffusion equation. And this equation is to show that, oh, this equation is good enough to obtain traveling wave phenomena. Okay. This is also a little bit interesting. This one is also a little bit related. So food metric diffusion. So if M is the amount of the food, then working distance should be given in this kind of way. In that case, diffusive gradient of D is given by this relation. So the diffusion equation with the O'Reilly's law is given like this. If you rewrite this like this, then you still have the advection term, which is exactly a logarithmic chemotaxis. Related papers also, we have some of the papers using this food metric idea. So, okay, let's just skip. Okay, so aggregation phenomena. Now we spent more work on this aggregation phenomena. So the first equation is the same diffusion. Now in that case, you can also consider here nonlinear diffusion or porous medium type diffusion, but with the heterogeneity here, departing probability gamma. Now for the aggregation phenomena, we have this equation. So V is the chemical produced by cell U. So this is the aggregation. Now this is the generation. So this one is the diffusion. So for this one, we have many related papers. So in the chemotext, for the aggregation phenomena case, one of the topic people are concentrated is to show the aggregation phenomena and the global existence together. So nowadays, we are more focused on this model, and then we are working on the global existence, for example, and aggregation. Okay, now conclusion. The heterogeneous diffusion can be applied to many situations. So I have two examples, two cases. One is the ecological invasion problems and the chemotaxis problems. But there could be more examples. If the claim here is that, oh, if you understand the diffusion better, then you can do many things better. So the heterogeneous diffusion model can improve theories in appropriate situations. Okay, that's the end of my talk. Thank you very much.
Please unmute your microphone. Mr. Kamruzama.
So much. Yeah, thank you so much. Okay, thank you, Professor Yang Jung Kim, and a warm congratulations for your nice presentations. You covered a wide area of diffusion from the basic law to the advanced level study. So now I will forward the question, answer, and appreciation session to Dr. Humayun Kabir. Before this forwarding, just I have a question. So then I'll forward for the audience. So what type of, especially for wild animals and for bird, what type of diffusion is more realistic? Either classical diffusion, I mean regular random diffusion, or starvation driven diffusion?
I'm sorry.
Yeah, I asked you about especially for wild animals and for birds, what type of diffusion is more realistic for their survival? Either the classical diffusion, I mean the regular diffusion, or the starvation driven diffusion?
So in a heterogeneous situation.
Right, definitely in a heterogeneous situation.
So that what is a regular diffusion? So you mean fixed law?
If yeah, right. Probably. Fixed law, right.
Yeah. So if you mean the fixed law, in the heterogeneous situation, then as I show, compare the result of SKT model, somehow you may obtain some wrong conclusion.
No
so so let me see. This one. Okay. So in this example, in this example, the SKT model, somehow they made a conclusion that in a bad situation, in a bad place, you should decrease your dispersal rate. You should stay there. Definitely that is wrong. Okay, why is wrong? Their analysis is correct, but what they use is so-called regular diffusion. And so in a heterogeneous situation, this diffusion may give you wrong conclusion. So here I used here more like Waray's law diffusion. Then this one gives you better result. Now instead of this Waray's law, if you use the starvation-driven diffusion, Then the one still gives you the correct diffusion, the correct conclusion.
Okay, so I have one supplementary question here. In the you just shown here a famous paper that's slow diffuser is the sole winner. That means they will prevail in Fick's law. So here we consider Rx is the growth function or carrying capacity, right? Yeah. So can carrying capacity or growth just can be negative or always positive?
Okay, so
yeah, so
you're talking about this model.
Next figure, right? This model, correct? For Rx, can be positive always or can be negative?
So some people use the equation in this form.
Right.
That means you have R here. Then in this setting, this R can be negative. It makes sense. Negative growth rate. Okay, so this is the case many people do. But if you rewrite this one in using in the shape of the logistic equation, then probably you may rewrite this one. Instead of this, you may write 1 minus U plus V divided by R. So if you put R in the denominator, then this R should be always positive. Okay, so it depends on the equation you choose. Okay.
Okay, thank you so much. Now I will request Dr. Humayun Kabir to conduct the question and answer sessions.
Thank you very much. Thank you very much, Dr. Kamruzzaman. So I have received a couple of questions. So Mr. Sajjad asked, can we apply this diffusion model in fractional derivative?
So fractional derivative is the one I never considered. Okay, so that's the question I cannot answer. So for the people who do the fractional derivative, people may use this kind of idea in the context, but I don't know. I never tried fractional derivatives.
Okay,
or
thank
fractional
you.
diffusion.
Okay, thank you. So Professor Molloy asked a question, how to identify bifurcation scenario for such models? Bifurcation analysis.
So in this equation, we have
probably he's asking about bifurcation scenario for the heterogeneous system. In case of heterogeneous diffusion.
So in this model, no. Okay, so this equation, for example, this gamma may have some heterogeneity, which is a function of starvation measure, like U over M or U over R. Then depending on the behavior of this gamma, this may produce, for example, Turing patterns more easily.
Exactly.
So if your interest is the bifurcation phenomena, then there could be many things that should be done, but I never considered the bifurcation phenomena seriously for this problem.
Okay, so he has another supplementary question. How successful invasion bifurcates from homogeneous steady state?
Homogeneous
steady state. How successful invasion bifurcates from homogeneous steady state?
Homogeneous situation?
Yes, homogeneous steady state.
Wait a second. So here I always consider the heterogeneous situation. The environment is heterogeneous. But for example, if you have R, then R is a function of X. Then steady state is always non-homogeneous.
Exactly. Yes, okay. So we can receive one or two quick questions from the audience if you have any questions. I can invite one or two quick questions.
Okay, so can I ask one more question, Dr. Humayun Kabir?
Yes, please. Yes, please, Dr. Kamruzzaman.
Okay, so Professor Kim, so already considered the homogeneous Neumann boundary condition, and we know there are a lot of good significance on that boundary condition. So why not the homogeneous Dirichlet boundary condition? And if so, what is the significance of Dirichlet homogeneous boundary condition for this type of model?
So for the boundary condition,
right? In all
so
the
so so
domains,
I always consider the zero flux boundary condition. So that is something I prefer. And some situations you may consider Dirichlet boundary condition, right?
When? Yeah, that's my point.
Yeah.
That's my question.
Yeah. So it depends on your interest. So if you use the Dirichlet boundary condition, the competition result may depend on the boundary condition. This Dirichlet boundary condition may dominate the evolution, right? So if you have a zero Dirichlet boundary condition, then the solution lose the population. There is some population loss on the boundary, right? So what my interest is to show the effect of the diffusion only. Okay, so I try to neutralize everything by giving the zero flux boundary condition, right? So but some people may be more interested in the Dirichlet boundary condition, and then it is a completely different problem, and then you may try.
Okay, thank you.
Maybe for the huge domain, there is a very nice influence of Dirichlet boundary condition. That's why, due to avoid that situation, we try to use the Neumann boundary condition. Because for huge domain, if we use the Dirichlet boundary condition, then it has an impact on the solution.
Yeah.
So in order to avoid this.
So if a domain is large enough,
yes, exactly.
And if you give the Dirichlet boundary condition, then you will get the same result as the zero flux boundary condition. But if your domain is small enough, then somehow this Dirichlet boundary condition dominates everything.
Everything, exactly. That is what I am saying. Okay, so the last question. What happens with time varying diffusivities? Time varying.
Okay. So I can tell you, I never tried time varying diffusivity. So my interest. So time varying diffusivity is another issue.
Okay.
So there are two ways. Diffusivity may constant in space and depending on time only. Okay, you may consider that case, but probably that is not that interesting. But if you consider the spatially heterogeneous and time varying diffusivity, then you will get some different story. Okay, but yes. To me, that is not the step yet. So I never considered that case.
Okay. So another question comes out, sorry. Could we consider to use your method for heterogeneous diffusion predator-prey model with sign chaining? Heterogeneous diffusive predator-prey model with sign chaining.
How come sign changing?
I don't know, maybe.
Okay, so forget about the sign changing part. So if applying this one in this kind of diffusion model to the predator-prey model, that's very promising. Actually, some of the papers I showed you, here, the first two papers by In-Kyung An, they consider this kind of diffusion equation for the predator-prey model. Okay, so if we use this kind of so you should be careful when you set the diffusivity. So how to set the starvation measure and plug into the equation. But setting the starvation measure is more important. But if you put this one correctly, then you will get some cross diffusion phenomena correctly. So for example, the predator somehow going towards the prey, and the prey will going against the predator. So this kind of diffusion theory will give this kind of cross diffusion phenomena correctly. So there could be many things you can do using this diffusion theory for the predator-prey case.
Okay. So thank you very much for your wonderful talk. We enjoyed a lot. So may I request to stop your presentation, to stop your slide sharing?
Okay. Okay.
Okay. So this is a small appreciation on behalf of Bangladesh Society for Mathematical Biology to Professor Youngjung Kim.
Thank
so
you.
Once again, I'd like to extend sincere thanks and gratitude on my personal behalf and on behalf of the society. Thank you very much for your wonderful talk.
Thank you.
Yeah. Okay, now I'd like to request Dr. Kamruzzaman to conclude this session.
So thank you again, Professor Dr. Youngjung Kim. Hopefully, near future will again invite you, and we'll our audience enjoyed your talk. So in near future again, we'll invite you, and you will just hopefully will just attend our conference either virtually or physically. So thank you again, and thank you the audience for the next session. Thank you so much.
Thank you very much. Thank you. So maybe Professor Haider Ali Bishwas, maybe we can have 10 minutes break to start the next session.
Okay, so this is the time for break, right?
Yes, yes. So we
so
can
our next
take
session will start at 5:30.
Not 5:30, 5:25.
Oh, 5:25.
5:25. 10 minutes break.
Okay.
Is that okay? Okay.
Okay.
So ladies and gentlemen, now we have 10 minutes break for virtual coffee. So thank you. We will be back on 5:25.
So I invite you to come and have a coffee in our campus. If you have.
Thank you.
Thank you very much. Thank you very much.
Because
why only coffee? You can invite for a dinner virtually.
No.
That's right. That's right.
Since you are inviting virtually, so you can offer grand dinner, so no problem.
That is in Khulna.
After the
Yeah, sure. I always invite for grand dinner, grand tea break, tea session in Khulna.
So when
we have accepted.
Will come after completion of the base.
Professor Haider Ali Bishwas invited us 20 times. So
yeah, and invitation will continue until we are not gathering.
Yes.
But
Thank you, and I have accepted this.
It never comes true. 20 times invitation, but never comes true.
Now,
my voice become very low.
Due to COVID-19, but we have planned to organize a meeting of BSMB Executive Committee in Khulna.
Yeah, sure.
Inshallah.
Yes,
Sundarban in Sundarban.
Inshallah,
yeah,
yes.
we can do the meeting in Sundarban, inside the Sundarban.
Sundarban, yes. No problem. Inshallah, we'll do.
Good idea.
Let's hope for this session, for this meeting event. I think in the coming year.
Okay, it's time for prayers, maybe.
Yes, yes, please carry on. Maybe we can.
Yeah. So I think
we can
in Khulna it
perform.
is.
Yes.
हाँ जी फरूक हो रहा है सही नहीं आ रहा अच्छा स्टेटमेंट लिखवाओ मुझे ट्राई करते हैं देखते हैं हाँ जी लिखवाएं लिखवाओ कॉज
Professor Kevin is here. Can you hear me, Professor Kevin? Can you hear me? I cannot hear you. No, I cannot hear you. Sorry. Sorry, Professor Kevin, I cannot hear you. Maybe there is some problem in your audio.
Check. How is that sounding now?
Yes. Now we
Okay.
can hear you.
Yeah, I think there was a problem with the microphone before. Yeah.
Okay. Welcome to our international e-conference, and thank you very much for accepting our invitation.
Thank you very much. Actually, I hope the next time I'll be able to visit in person. Actually, very much. But it's a pleasure to be here, even if virtually.
Thank you very much. So now you are in Politecnico di Torino.
That's correct. Yes, I moved there start of October, basically. So
I see. So when you moved to Torino? This year or?
Yes, just 3 months ago, basically now. So
quite recent.
Very recent, yeah. So I'm still finding my way around it. Yes.
Oh, thank you.
I decided to get you said about a virtual coffee, so I decided to, this is actually decaffeinated, so I would call that virtual coffee as well, actually. So
thank you very much. Okay, maybe we can start. Mamun sir, can you hear me?
Yes, I'm hearing you.
Okay, so let's start. Ladies and gentlemen, welcome back to our third scientific session today. So the keynote speaker of this session is Professor Dr. Kevin Painter. He is from Politecnico di Torino, Italy. So first of all, on my personal behalf and on behalf of the society, I would like to extend our sincere thanks to Professor Kevin Painter for accepting our invitation. And he has given his kind consent to give a talk here. And really, we are thankful to him. So probably last year we met in Oxford, and before that, once we met in Meiji University, Japan. So probably after COVID-19, we can meet anywhere of the world. Okay, thank you very much. So this session is chaired by Professor Dr. Muhammad Mamun Mullah from North-South University, Bangladesh. Professor Mahmoud Mullah is one of the founding members of Bangladesh Society for Mathematical Biology, and he is also serving an executive member of this society. Now, I'd like to request Professor Dr. Mahmoud Mullah to conduct this session. Now, over to Professor Dr. Mahmoud Mullah.
Thank you, Dr. Humayun. Before inviting to Professor Kevin Painter, I want to introduce himself. Professor Dr. Kevin Painter, Inter-University Department of Regional and Urban Studies and Planning, DIST, Politecnico di Torino, Italy. And now the short biography of the Professor Kevin Painter. Professor Kevin Painter is currently a professor at Inter-University Department of Regional and Urban Studies and Planning, Politecnico di Torino, Italy. Dr. Kevin was a professor at the Department of Mathematics and Maxwell Institute, Heriot-Watt University, UK. Professor Kevin achieved his DPhil from the University of Oxford under the supervision of Professor Philip Kemeny. His research interest involved formulating, analyzing, and applying mathematical and computational models to biological process. He's particularly interested in how patterns arise in nature, such as pigmentation patterns on animals, and how animals and cells find their way through their environments. Professor Kevin was awarded Lever-Hulme Trust Prize, Research Fellowship, and Cambridge Philosophical Society Bursary Prize. He has been serving in the editorial board of Discrete and Continuous Dynamical System B. He was a cohort director of Maxwell Institute Graduate School in Analysis and Applications. He served as a management group member at Center for Systems Biology at Edinburgh, CSVE, and as a board member at Edinburgh Mathematical Society, EMC. Professor Kevin has given many invited lecture series all over the world. He has also written a good number of very well-received expository papers and monographs related to mathematical modeling and pattern formation in biology. Now, I'd like to cordially invite Professor Kevin to deliver his valuable speech to the audience. Now,
thank you very much for the introduction. Thank you very much. I'll just start sharing my screen. Okay, is my screen being shared now?
Yeah.
Okay, thank you very much for the introduction. It's a pleasure to come and speak about my work today. Actually, it fits very well with the previous talk. I'm going to also be talking a little bit about diffusion models, but a slight variation in terms of the type of diffusion models that we're going to look at and the type of problems that I'm going to be looking at. So this is work with various collaborators over the last decade, principally Professor Thomas Hillen at the University of Alberta. So he's been my principal collaborator on this work. So I'll start with a few slides of biological motivation. And this is particularly to do with how cells orient according to their environment. So it's well known that certain cells, when they migrate, they will respond to what we call the anisotropy of their spatial environment. This kind of top video here, and I'll show the video in a moment, shows fibroblast cells that have been put onto certain surfaces. This one on the left is effectively a homogeneous surface, so there's no real heterogeneity in that environment. This one on the right, you can probably see some very faint horizontal lines along it, and this is creating an anisotropic oriented structure. And these are basically little ridges which allow the cells to orient. And when you kind of follow the pathways of cells, you see that according to their environment, they will either form kind of effectively migrate along that direction, as in the right, or migrate in a fairly random direction, as we see on the left. So, in other words, that environment of the cells has a strong impact on influencing the direction of migration. And that can also be seen in sort of this sort of scenario here. You have, again, a similar sort of structure where cells have been placed on environments. You've got regions of what we call one-dimensional here, where lines are oriented in one direction, a region of either a crisscross or a kind of a blank region here. And as the cells migrate those different types of environment, they will change their behavior accordingly. So the key point is that cells will orient according to anisotropic structure in their environment. Now, why is this an important phenomenon? Well, these are experiments that are done in what we call an in vitro system, where basically we're looking at migration for cells that have been removed from the body and put on a kind of a particular surface. But the significance of this is that, of course, inside our bodies, we have a lot of very complex environments. And for example, if you look at the kind of what we call the connective tissue, so an example of that would be the dermis of our skin. The dermis consists of a lot of collagen fibers, and they can take a very aligned format. And cancer cells will align according to those collagen fibers and migrate along particular directions accordingly. Similarly, if you look inside the central nervous system of the brain, again, this is what we call a highly anisotropic environment. We have various neurons that are connecting different regions to the brain. Those neurons are connected by these long blue axon fibers. These are basically kind of like a long cable along which signals of the brain are passed. And glioma cancer cells use these long bundled axons as highways for facilitating their invasion. So it's obviously of manifest interest to understand how cells are responding to their environment. The reason then for looking at this is then very much connected with then understanding the way a cancer will spread through the brain. And the one I'm going to be talking about later is a class of brain tumor, glioblastomas. And glioblastomas are highly diffuse, aggressive, and heterogeneous tumors. So this is an MRI scan of a glioma. The cancer itself, it's not really this white stuff that you're kind of seeing here. It's slightly, you can't quite really see it, but basically the key point is that the cancer has a highly heterogeneous shape, and the problem for clinicians trying to treat this disease is that there is a large proportion of this cancer that is invisible through this type of imaging scan. So because the cells are very small and they migrate away from the main glioma mass, there's a large invisible component. And it's believed that one of the reasons for this complex pattern of invasion is that the cells are using the oriented structures of the brain to migrate. Those are kind of my motivating problems, to understand what is affecting the way the cancer migrates. Now, what sort of data do we have to understand this problem? You can classify it into two different scales. On one scale, you have what we call microscopic data. So these are where basically you track individual cells. What we're seeing here is a plate where we've got a mixture of kind of nerve cells and cancerous glioma cells. And these sort of studies allow us to sort of see how one of these cancerous cells migrates along these axon cables. So you can't quite, they're these very little dots that you occasionally see running along a fiber. They're gripping along to that axon and they're migrating accordingly. So this is what we call individual cell level data. It gives information on how quickly cells move, what their turning rates are, and how they respond to the environment. And then the other sort of type of data we have is what we would call macroscopic data. And that's what you can get from imaging such as this, where you kind of get a large scale picture of the growth of a tumor. And this is, of course, at the scale of billions and billions of cells. And this is very different spatial scales. And we'd like to have models that can exploit the data at these different levels. So how can we kind of marry together this microscopic and macroscopic aspect? So, and again, sorry, another slide here that is again just showing this sort of behavior of cells in terms of orienting according to the anisotropic structure of the brain. So I'm going to talk, as I say, about in the rest of this talk about kind of 3 levels of model that we use to study these types of problem. I'm going to start with an individual random walk model. And this is basically at the scale of my individual cells. So it describes how a cell is moving locally within its environment. And the advantage of this model is because we have data at the same level, we can study that from the movement pathways of cells. So it allows relatively straightforward parameterization. The problem, of course, is it's computationally very intensive. We're studying a single cell here, basically. A large-scale tumor, such as a glioma, is about 1 billion cells. So we couldn't computationally study an entire glioma with this method. I'll then talk about a mesoscopic transport model, which is a continuous model. So therefore, it can be analyzed, but it still is at the cell scale. So it's still describing this kind of local scale movement type process. And again, the problem then with that one is it still becomes very computationally intensive to study. And then I'll talk about a kind of fully macroscopic model that allows me to study this kind of very large scale phenomena of how a cancer is spreading in a brain. And the key is that we're going to use scaling methodologies so that we start with this individual random walk model and we scale up to a full macroscopic model. So what's our modeling methodology for doing this? Well, it's what we call a velocity jump random walk model. And these models were kind of got their kind of roots in the work of Patlak in the 50s, and then very much popularized by the works of Alt and Othmer in the 1980s. But basically, it describes the movement of some particle. It could be a cell, it could be an animal, but effectively it describes it as a process of running and tumbling. So the particle moves through space in a run, and then with some frequency, it changes into a tumbling mode, changes its orientation, and then runs, tumbles, runs. So it's what we call a velocity jump random walk. You make basically a kind of a sequence of runs and tumbles through space. So that's the velocity jump random walk, but you can actually you can formalize it in sort of various sort of ways in terms of how to set it up. And we're going to try and choose the simplest possible formulation that allows us to consider how an individual running through this random walk can respond to environmental information. So we make a few assumptions. We assume that the rate at which you make a turn is a constant. So the kind of effectively, you know, there's going to be, you kind of make a turn at a, you know, roughly every sort of time interval of, say, every second or something. Once every second we make a turn. We assume that that tumbling is quasi-instantaneous. We assume the speed is constant. And what this kind of allows us then is just to concentrate on effectively a single aspect, this Q, which is effectively a probability distribution for choosing a new velocity V each time we do one of these tumbles. And this Q is therefore the key point where we can incorporate environmental factors. So through this Q, that allows us to effectively incorporate some sort of effect of the environment in terms of telling a cell where it's going to go. That's our minimal formulation, and that's the individual velocity jump random walk model that we use. And as I say, from that, we can write down what we call a mesoscopic transport equation. And this comes from an assumption that we have effectively negligible interactions. That's a big assumption, I should say, but you know, it's an assumption that we're going to make. And this is now effectively a continuous description of that previous individual random walk model. So we've got a continuous variable, which is our kind of particle density, our cell density. And this is a cell density that is structured in time t, position x, and velocity v. And if you look at this equation, you'll see it's got a fairly straightforward form. This kind of term here is effectively my running term. So my cells are running through with some velocity v. And then these right-hand terms here is my turning process. So with some constant rate mu, I do a turn, I move away from velocity v, and then I have, of course, other particles that are coming in that are choosing my velocity v. So from all other velocities v dash, I can choose the velocity v. So this mesoscopic transport model is just effectively a continuous formulation of that velocity jump random walk. We've got my run in this transport term here, and the right-hand side is doing my turning process, either turning away from velocity v or turning into velocity v from all other velocities. That's the mesoscopic transport model, and we can make even a further simplification. We can assume that my new velocity becomes independent of my previous velocity. So that kind of Q doesn't depend now on V dash, basically. It's just going to be, it just depends on time and space. And then I'm going to come up with an important new variable M, which is my macroscopic density. And this is my population integrated over all possible velocities. And this is effectively, this macroscopic density is what we would see as the density of my particles at a particular point in space. So I'm not looking anymore about their structuring in velocity. It's just my macroscopic density, the density that I see in a particular volume of space at a particular time. And to get to a macroscopic model, well, sorry, before I say that, once we kind of define this M, this transport equation model becomes even simpler here, basically, because this Q now no longer depends on V dash, so I can kind of bring that out, and I get this kind of very similar transport model here. But this mesoscopic model, as I say, is still quite computationally intensive because we've got we've got a kind of a particle density that depends on time, position, and velocity. So we'd much rather get a single evolution equation for this macroscopic density M. So that's what we would like to do. So how can you derive a macroscopic evolution equation for M from this transport equation? Well, there's various ways of doing it. This transport equation is another term for that is a kind of a kinetic model, but basically you can apply various sort of techniques, moment closure, hyperbolic scaling, a parabolic scaling, and in a kind of a review type article with my collaborator Thomas Hillen, we kind of discuss these three different sort of approaches. But basically you can apply these and derive a kind of a macroscopic equation, which is of course more analytically amenable. So I'm going to show how to do this using this moment closure method. I'll go through this relatively quickly, but of course, if you do want to see the details, then I can point you in the direction of that paper where we looked at this. So you start with your kinetic transport equation and remark that Q is a probability distribution. It's by probability of choosing some sort of velocity, so it has the characteristics of a probability distribution. We're going to define a few things. We're going to describe the expectation of Q and the variance, covariance matrix of Q. Those are kind of standard statistical properties of my probability distribution. We're going to define a similar set of quantities for my P. P is not actually a probability distribution, but we can normalize it to by setting P hat to be P over M. And then I can also describe the expectation of that P hat and the variance covariance matrix of P hat. And of course, what we're going to try and obtain is an evolution equation for M. So our kind of first step is to take that transport equation and integrate with respect to V, so a standard sort of integration process. And then that kind of just does standard integration to all of these terms here. And we can kind of note that, note from the properties of, the way we defined M is basically this kind of, this integral here. Q is a probability distribution, so that just integrates to 1. And actually what that therefore gives is the right-hand side terms here are going to cancel. And then when we do that, we get a conservation law for M. So this is now an evolution equation for M, but it depends now on this expectation of this P hat. So we need an equation for this EP hat in order to solve this conservation law. How can you do that? Well, let's go back to that transport equation, multiply by V, and then integrate that with respect to V. So you kind of go through a similar sort of process. The equation now starts to get a little bit more complicated, but you can do a little bit of rewriting. I don't want to go through the details here. They are in that paper that I did, but you can kind of rewrite that sort of equation and, again, kind of rewrite certain sort of properties, do a little bit of kind of standard sort of calculus on those sort of various things. And when you kind of put all of that together, you do get an evolution equation that would allow me to solve EP hat, but it now depends on something new. It depends on this variance covariance matrix, this V. And this kind of then illustrates the problem of this moments method, because the first equation we got was a conservation equation for M, but that depended on EP hat. We then got an equation that would allow me to work out EP hat, but that depends on an even higher moment, the variance covariance matrix. And effectively, what you kind of do through this sort of process is you generate just an infinite sequence of higher order moments. So in order to stop this process, you need a way to close it. Well, you need a moment closure assumption. We assume two assumptions, which are fairly standard ones. We assume that this variance is computed from the equilibrium distribution. And secondly, we assume what's called a fast flux relaxation, which assumes that the second equation is in a quasi-equilibrium. And basically, the interpretation of this is that at the space and time scales of your problem, your individuals are effectively responding immediately to the environment they see. But without kind of going into all of the details, what these kind of techniques kind of allow us to do is obtain a macroscopic equation for M. And this will now probably seem a lot more familiar to a lot of people because it's of the form of a drift diffusion equation. So M is, of course, my macroscopic density. It's what I want to solve. We've got a drift term here. It's got an advective velocity A. And this right-hand side is effectively a diffusion term, but it's a lot more complicated than the sort of diffusion terms that you probably see in kind of classical reaction diffusion models, because this is what we call a fully anisotropic diffusion. This D here is a diffusion tensor matrix. And the diffusion tensor matrix is basically saying is that diffusion is can potentially be taking place very quickly along certain directions and much more slowly along other directions. So it incorporates an anisotropic diffusion process. In the previous talk, those diffusion coefficients that were being looked at were isotropic. So they could be heterogeneous in space, but they were isotropic in terms of the spread. This is an anisotropic diffusion tensor process. But the whole, as I say, point of this is that these A and these D are parameterized by what we put into our individual random walk model. They just depend on that Q that we put into that sort of model. And I could choose a Q and a kind of a standard thing. Q is effectively a directional distribution. And that Q can kind of come into that sort of model as a kind of a way of choosing some sort of dominant direction with some concentration parameter. And because we have a clear analytical way of then calculating my A and my D, according to the parameters of that Q distribution, I can explicitly calculate the coefficients for my partial differential equation model. So the upshot is, as I say, is that we basically have a way of connecting from individual level detail of how an individual is moving through space to what we put into some macroscopic diffusion, anisotropic diffusion type model. Okay, so that's kind of the methodology that we use. And as I say, there's a lot of details there, but I'm happy to refer you to papers if you are interested in that sort of problem. So how would this then apply to biological data sets? Well, we're going to start with a kind of a test study. So, and this is going to be similar to some of those sort of studies earlier, basically, where they do these sort of things. They take cells from their kind of tissue environment and they plate them on some oriented structure. And they can plate them on different ones. So you could plate them along here where you've got just kind of long lines, basically. Plate here where there's kind of more of a crisscross, but there's still a kind of a slightly dominating alignment, to out here where you've got effectively kind of a complete crisscross structure. So they can create these through kind of nano engineering sort of methods, basically, to create these environments. And then they put the cells onto this environment, and according to that environment, they can follow their orientational structure. So in those different sort of regions, they will become either more aligned or less aligned according to that environment. So this is a kind of the sort of study that we can, sort of data that we can look at. The way we could do this in our model is, well, we basically need to kind of choose some Q, and Q, as I say, is basically, it's my kind of indication, it's kind of the way I'm incorporating navigation in response to the environment. And I'm going to choose what's called this bimodal von Mises distribution. And it will basically say that if my cell is in this region here, then if I have a kind of a large value of this K, this concentration parameter, then I'm highly likely to choose either this direction theta, so up the fibers, or down the fibers. So that's what this kind of Q does. And we can take that cell orientation data in there. We can, based on that cell orientation data, we can work out what the value of K would be, fit that into my Q, and that will say then that for that kind of individual random walk model, then you kind of choose either as, say, the up or the down directions. They're likely, when they tumble and choose a new direction, they're going to follow that alignment. Or if I'm in one of these regions here, which looks kind of much more isotropic, then the cellular orientation data there will give me a much smaller value of K. I put that into my Q and I get more of this sort of pattern of movement. So that's what goes into my individual random walk model. And then, of course, from that Q, I can work out what the diffusion tensor matrix would be in my macroscopic model. That's a kind of a standard calculation, but which one can do. It's a bit of a tedious calculation, but it gives me, as I say, my inputs for my macroscopic model. And this effectively then kind of allows me to go from experimental data over here, where we've got the kind of the individual cell paths. We parameterize that into our velocity jump random walk model and effectively recreate those individual kind of pathways. And then from that, we get a macroscopic PDE description. So it allows me to kind of look across these different scales. So that's the kind of the underlying framework. Okay, so let's now kind of then move to some of the actual applications that we'd like to use this to study. Well, I'll start off with, we're talking a little bit about how cells move through environments. So cells in our body will move through a lot of the time. We've got a lot of cells that all of the time are moving through the extracellular matrix that forms much of our tissues. So if you kind of go to the skin, you have the top layer, the epidermis, but below that, you have the dermal tissue. And that kind of dermis there is actually mainly composed of extracellular matrix. And that extracellular matrix is basically formed from various proteins that form this kind of mesh scaffold type environment. And the cells in the dermis, such as immune cells, fibroblast cells, will migrate through this. And this is, of course, very important for kind of immunosurveillance, so kind of finding out infections. It's important when it comes to wound healing. And of course, it also has a kind of a sinister side when it comes to processes such as cancer invasion. But different cells will employ different sort of strategies. And in one type of strategy, what we call amoeboid migration, this is a very fast strategy. Cells will follow these fibers. So when you kind of track a cell, it will basically be following along these individual collagen fibers. They form this mesh sort of structures. They follow them along, but they don't fundamentally change the structure of the ECM. So it doesn't really kind of alter things very much. That's my kind of amoeboid migration. And then on the other hand, there's a kind of another type of migration, which we call mesenchymal migration. And in that type of movement, the cell will move through the ECM, but as it moves through, it also changes the matrix environment. And in particular, as a cell is migrating through, it orients the fibers in the direction in which it is traveling. So you can see in this picture here, in this right-hand side, this cell is moving kind of from down here to up here, and the fibers that are kind of being oriented in its path. So these two kind of modes of migration, amoeboid and mesenchymal migration, have different impacts on the matrix environment. In the first case, the cells follow the fibers, but they don't change it. In the second case, they follow the fibers, but they also realign it as they're moving through it. So let's kind of look at some kind of modeling things. And the first thing to point out is the ECM changes a lot in terms of its structure. So if you look in certain tissues, the ECM is kind of highly unoriented. It's kind of just fibers in a fairly sort of random arrangement. In other regions, the fibers may be highly aligned, or in other regions, actually, it may have kind of local alignment, but overall, a kind of a less, less structured sort of environment. But the fundamental point is that these kind of ECM, the alignment of this ECM can change a lot from tissue to tissue. So the question would be is how does this kind of process of following along these fibers, how does that impact on invasion pathways? And this is then potentially very important when it comes to cancer invasion, because when you look at sort of cancers and basically in these sort of pictures, my cancer, my solid tumor itself is in this top left of each of these frames. So this kind of, in this kind of top left here, we kind of see the solid tumor itself here. And then around here is this kind of extra cancer space, and it consists of collagen fibers. In benign cancers, those fibers are aligned or aligned parallel to the tumor interface. So the tumor interface here and the fibers are aligned parallel to it. In more malignant cancers, they tend to be aligned in an orthogonal direction. So there's a different alignment in those sort of two cases, and that could potentially have a very significant effect on cancer invasion. So we model that with our kind of framework. So we kind of have a tumor in the middle here, and we consider either my environment to kind of encapsulate it, to have fibers that are kind of sort of simply in a kind of a parallel to the tumor interface. We have them in a kind of an orthogonal interface in this radial section, and a kind of a random structure there. And we study a model for cancer invasion, and you get very different rates of invasion. In that kind of case there, where you've got the encapsulating, then you get very minimal cancer invasion. The cells are unable to infiltrate that because they're orienting according to the structure. In the radial case, that kind of much more malignant type cancer, you get a much faster rate of invasion. The alignment could then potentially have a big impact on the rate of the invasion of cells. Okay, and that sort of observation seems to be seen in studies on the kind of the rate of infiltration of cancer cells in for different types of cancers according to the local environment. Okay, so that's kind of our first sort of point. And the second sort of point is that this model, these kind of model simulations also imply that you can get through this kind of drift anisotropic diffusion model, you can get a lot of structuring of your population. So the way fibers are arranged can allow your population to become structured in a particularly heterogeneous way. So when you kind of have a kind of a region of kind of random matrix, but then in the center, highly aligned fibers, your population becomes organized onto that region. Or similarly, in a kind of a radial structure, you can get a concentration of the population according to the environment. So that kind of heterogeneous anisotropic nature of the environment can act to kind of group your population together in a particular way. And I'll do a little bit of an ecological diversion at this sort of point. And this is a kind of a study on, and this is kind of to do with kind of the behavior of wolves and caribou on seismic lines. So this is a problem that people like Mark Lewis and colleagues have looked at a lot. But the problem here is this is a problem in kind of northern Canada, basically in Alberta, where there's a lot of oil exploration. And in particular, what the oil companies do are they kind of cut long paths into the boreal forest. So this is an aerial view here. The kind of green is kind of the boreal forest. And these, you see these kind of lines here, and these are kind of pathways of cleared vegetation, which the oil exploration companies use basically to then test for oil. Now, this kind of impact in the environment has changed the population dynamics of wolves and caribou. The wolves, basically, when they encounter these seismic lines, they reorientate themselves along it and they move along them. So there's an orientation according to these linear features in the environment. And that's allowed them to become more efficient at finding this caribou prey because they can cover quickly large tracts of the environment. So our kind of model, basically, we can kind of use this to study these sort of problems. So we kind of have as a model for kind of wolf movement. We assume that they're kind of random when they're away from the seismic lines. And then when they're on the seismic lines, they orient themselves according to it and move along their direction. So then you can kind of take this sort of, you could take a sort of a typical sort of environment. You can kind of add in these kind of seismic lines to them into that environment. That is then parameterized for our kind of wolf movement patterns. You solve the macroscopic equation. This is just simply this anisotropic diffusion equation up here, but it's got this complex anisotropic diffusion structure. And the wolf distribution goes from being homogeneous to becoming concentrated along the seismic lines. So, as I say, even though this is just a very simple looking, innocuous looking kind of diffusion type model, it can actually give rise to kind of high structuring of my population. And as a kind of a potential extension of this model, we'd like to then kind of incorporate this with the movements of the caribou and then include population dynamics between these populations. Okay, so that was kind of one aspect. I probably won't talk about that one. I'll go on to this one. That was kind of describing that kind of amoeboid type movement processes, basically. And what I mean by that is that we were kind of responding to the orientational structure in the environment, but we weren't changing it. But mesenchymal migration is a different sort of process. And in that one, basically, as my individual moves through the environment, it aligns it, it changes the structure. So we can also study those sort of problems with our model and with our kind of transporter equation, what it kind of means. I won't show you the exact equations for this, but that kind of Q now becomes time dependent according to another variable, which is describing how my environment, my matrix fibers are evolving. This Q depends on my extracellular matrix, and that's being realigned due to the movement process. I won't show you the equations themselves, but I'm happy to kind of, they're in a paper of 2009 if you want to follow that. So what happens when you get that sort of behavior? Well, in that case, we're going to start with a case where my cells are uniformly distributed. So the gray is my kind of macroscopic cell density, and it's kind of uniform gray here. And my environment, my fibers, are basically kind of indicated by the orientation of these kind of little lines here. So this is kind of what we call a kind of a uniform, this is kind of a completely homogeneous starting point. All of my cells are homogeneously distributed, and the matrix is completely non-oriented. So there's no kind of alignment there. We run the model and we get a process of spatial pattern formation. The cells realign the matrix environment, and then they kind of organize themselves into high density, these kind of red regions, high density cell chains of moving, and these are kind of cells that are moving around and aligning that environment and creating effectively cellular pathways of kind of high density cell movements. This is a self-organization process in the model. We start from a completely homogeneous and non-aligned starting point, but we get pattern formation coming out of this, where the cells align their environment, reorient it in their direction of movement, and create these kind of patterns of cell, kind of high high density cell patterns. So that seems to be a pattern formation process, and it's kind of quite interesting to note that vascular genesis seems to show a similar sort of behavior. So they've studied this kind of in the formation of the blood capillary network. When you kind of analyze the movements of endothelial cells that form our blood capillaries, they basically seem to form similar type network structures, where basically along these kind of lines here, you have cells moving along this sort of way, along kind of particular sort of pathways. So possibly this sort of early vascular genesis process could be through this feedback in which cell migration is coupled to remodeling the matrix environment. And we have it, and this is kind of a pattern formation problem, and I think there's some interesting questions there about kind of really understanding this through using kind of stability analysis techniques. Okay, so that's kind of then the third case, but let's now kind of move that to the final application. And I think this will be about, I'll go through this quite sort of quickly. And this is a kind of an application now to glioblastomas. So I talked about this sort of problem earlier. So glioblastomas are these kind of particularly nasty brain cancers. They're highly malignant cancers, and they're formed from the brain's glial cells. And basically the problem with this kind of cancer is that cells, once they kind of evolve to this kind of most malignant form, they become highly migratory, and they invade and infiltrate the surrounding healthy brain. So the way kind of treatment is done for this at the moment is the clinicians will take an MRI scan, and they will identify from that what they call the gross tumor volume. So that's where they think the majority of the tumor is lying. But then, because they know that the cancer cells are very invasive, and that even though this is what they can actually see from imaging, for the treatment, they consider a larger area, what they call the clinical tumor volume, and it's set as basically 2 centimeters from this gross tumor volume. And that's where, over that dashed region, that's where they will apply their imaging. And that's, of course, a very logical process in order to try and sort of capture these cells that have escaped from the main tumor mass. But the problem is actually this tumor grows in a very complex way, and that border will be highly heterogeneous. And some cells will actually have escaped beyond that kind of treated region into these kind of points here, and those will be untreated, and then they will be able to grow into a cancer again once treatment has ended. And indeed, that's what happens then to many of the patients that have been unfortunate enough to be diagnosed with this disease. So we would like to have better models to actually predict this invasion of these cancers. Now, where this kind of fits in with our earlier, and I kind of mentioned this earlier, in fact, the glioma cells basically migrate along these kind of long bundled axons of the brain. So because in the brain, we've got lots and lots of kind of neural fibers. And if you do a map of the brain, you can see these kind of long axon cables that are connecting neurons. They form a highly anisotropic sort of structure, and they're kind of bundled in particular sort of ways. But fortunately, we've got imaging techniques that are basically able to do a scan of the brain and parameterize this to get a map of this anisotropic structure. And this is through a kind of a process of diffusion tensor imaging. So it basically provides a map of this anisotropic structure of the brain. And that diffusion tensor imaging basically relates to kind of the movement of kind of water molecules. It gives rise to kind of a diffusion tensor matrix, And the water molecule, the diffusion of the water molecules is anisotropic, so it kind of diffuses in certain ways, and that in turn tells me where the fibers are bundled in particular directions. So we've kind of studied this model, and in fact, it's been a problem that's been studied by various people, but basically our kind of approach here is basically to kind of take in that macroscopic data input, that kind of imaging that we get from diffusion tensor imaging, and that kind of feeds into kind of our behavior of our cells. And then from that behavior of the cells, we then obtain a kind of a macroscopic diffusion model for our model. And it's got the form of it's basically a Fisher equation, but now with anisotropic diffusion. So this kind of more complicated diffusion process. And that's all the model that we can solve here. That's kind of the model we sort of solve. And we can simulate this in kind of artificial sort of setups, basically, where we consider kind of effectively a random environment, but certain regions.
Professor Kevin, we have some time restriction, please.
Okay, yeah, I'm coming to the end actually, so it's about another
minute
or so, basically. Yeah. Okay. Yeah. Okay. So we kind of have this sort of case here, where basically we have these kind of crisscross fibers. And if we have no fiber following, you just get a kind of a symmetrically growing tumor, which kind of spreads out, which was what we would expect from the Fisher equation. But if we have fiber following, they start to follow these crisscrossed fibers. But that's within an artificial setup. But we can do this with kind of real DTI imaging, and that gives rise to this kind of complex heterogeneous pattern of spread. And my colleagues now, Thomas Hillen and colleagues, are now kind of taking this and starting to fit this against clinical data. And they're basically kind of taking this sort of model. I'm not going to describe this because this is work by my colleagues, but then they're kind of looking at comparing against other models for this and finding that this kind of new model seems to give a better fit to data on average. So to summarize, what I've kind of talked about is this kind of framework that we're looking at to study this kind of multi-scale sort of framework. And basically, this kind of allows us to go connect from individual to kind of macroscopic models. We're now using this to kind of try and apply to kind of models to glioma invasion. But a fundamental sort of philosophy that we kind of have in this is to try and keep the model as simple as you can. So that individual velocity jump random walk, we try to keep it as simple as you can. Of course, eventually things will become more complex, and then you have to go back to reassessing those underlying models. So I'll finish at that point there. Thank you very much for your time, and happily accept any questions that you may have.
Thank you very much, Professor Kevin, for your nice presentation and valuable work. Just one quick question from me. You mentioned that you prefer to use the macroscopic model. And another thing we described that mesoscopic model. And you mentioned that the mesoscopic model is a time intensive, but is time intensive?
The
model.
Yes. Yeah, the mesoscopic model.
Mesoscopic. If you solve the macroscopic model, then this is a very complicated equation, the second order equation. And for the probability density function, M, you have to solve another equation. But if you solve in a mesoscopic equation, I think you have to solve only one equation, and this is a first order differential equation, and no need to solve for M.
Yeah.
Am I right?
So the mesoscopic, yes, absolutely. No, that's a very good question. And in fact, actually, that's why we have these kind of 3 different scales, because each of them have their different advantages. So my mesoscopic model kind of looks like, say like this sort of form here, basically. The problem with this one is that it's still, if you want to solve this computationally, it's still very intensive because my P is structured in time, position, and velocity. So yeah, if you're thinking about kind of trying to solve a kind of a three-dimensional environment, actually to kind of, say, use a finite volume scheme or a finite difference scheme, you would have to discretize over your three space dimensions and also your three velocity dimensions. So that becomes completely impractical for this kind of glioma type sort of problem in order to do that. So it has the advantage, and in fact, actually, you can try and analyze this sort of model as well. You can try and study this sort of problem here. In fact, when I was kind of talking about this pattern formation problem, this was actually a mesoscopic phenomenon. So this was a simulation of the mesoscopic model and not the macroscopic model. When you try and do this in the macroscopic model, you don't get this sort of pattern formation. So it contains detail that you lose in the macroscopic model, but it still can be very computationally intensive. So the good thing about having the different models is that you can try and study a problem using these different sort of ways of looking at it.
Okay, another supplementary question that in this mesoscopic model, the particle can move randomly, or you have chosen the different specific model?
In the individual velocity jump random walk model, that's a kind of a stochastic random walk model. Each time it does a tumble, it chooses a new direction according to some probability distribution, but it's a kind of a random selection of that. That mesoscopic model is a deterministic model. It depends on kind of a probability distribution, but it's a deterministic model. Yes. Yeah.
Okay, thank you. Now I'm handing over to Dr. Humayun Kabir for the discussion and question session. Thank you very much.
Thank you very much, Professor Dr. Mamun Mullah. First of all, I'd like to thank Professor Kevin Painter for his wonderful talk. So probably Professor Kim is here. Professor Kim has a question. So now over to Professor Kim to ask you a question. Professor Youngjung Kim. Professor Youngjung Kim, are you here?
Yeah, I'm sorry.
Yes, please ask your question. Please ask your question.
Actually, I thought you're going to ask instead of me, so.
Okay, no, you can ask. Then it would be better, I think. Sorry.
Okay. So the question was this. It was great if the turning frequency mu and the cell speed v can be obtained together. And my question is, I think you consider the turning frequency mu is constant. If mu is not constant, then the resulting equation will be different. So my question is there some reason why you consider constant turning frequency mu?
Okay, I kind of didn't quite sort of get to this sort of point. So we do it in order to start with to try and have the simplest possible model, basically. So the only thing that was kind of affecting my movement paths with this Q, so that we could just focus on one thing. Now, as you say, I showed these sort of slides here, these kind of behaviors of cells on these sort of different sort of surfaces. And these show two very different behaviors according to what happens when they kind of reach this sort of middle region. And when we have that constant turning rate choice, we can't differentiate between those two cases. And actually, when you have a non-constant turning rate, you can actually capture that sort of behavior. So, basically, that would be exactly this sort of case. You try and keep it as simple as it can until the model as simple as it can, but at a certain point, the model will fail because, of course, cells or indeed if organisms will behave more complicated. And we've actually just finished a study having this kind of non-constant turning rates and deriving that the macroscopic model becomes more complex in that case, as you would expect, but of course it actually then allows us to kind of incorporate more detail into these processes. But yes, absolutely, that's a very kind of important sort of point. Yeah, try and keep the model as simple as you can until you can't. Basically, is the philosophy.
Okay, thank you very much. So, Mr. Arindam Pal, you have a question. Mr. Arindam Pal, are you here?
Sir, I'm here.
Yes, please ask your question.
Sir, thanks for giving a chance for asking a question actually. I have seen some of your works on from pattern. Pattern means from image patterns or matrix to mathematical models actually. I noticed your work on diffusion modeling in several level. Can you discuss something or suggest me something for modeling any pattern of any images which has a flow actually, which is changing over the time, and it's not it's the change, suppose the change is for only 30 or 40 seconds maximum, and I want to model, if I want to model the pattern from images to mathematical equations, what should I do, or what types of methods should I use there? And I can extract any features of images, and I can form any types of metrics if needed actually. I just need a direction for deriving mathematical models from the data. Thanks a lot.
Yeah, okay. So yes, this, I think that's the perfect sort of application for this sort of model, because as I say, that individual velocity jump random walk model does allow you to parameterize that kind of biological data set. Yes.
Sir, I just want to learn some, I just want some suggestions from you so that I can make a mathematical model from the patterns. I can model the patterns mathematically actually. I want to say what types of methods should would you want to suggest me? What types of methods are being used?
So I think I could probably spend quite a lot of time answering that. So I if you don't mind, I would recommend that you send me an email, and then I can provide a little bit more of a detailed sort of response and potentially some sort of good references to have a look at. So
thanks a lot, sir. Thanks a lot.
Okay, thank you very much. So the last question is, Mr. Ratish wants to know, how is the time scales for such a dense cell pattern formation? How is the time scale?
Again, this is something that when you move from the individual velocity jump random walk model to the macroscopic model, you're basically moving, you're kind of scaling across space and time when you kind of go through those transitions. So in that kind of individual, in that kind of very kind of microscopic scale movement, your model is described in terms of kind of the time scales of an individual cell moving. So it's kind of moving across a distance of like, 10 microns, 100 microns, basically. And it's kind of making a turn on a kind of a scale, turns at a frequency of maybe, once a minute or something like that. So the time scales for those kind of underlying mesoscopic or velocity jump random walk models is on a kind of a scale of microns and minutes. The macroscopic model is on a time scale of, kind of centimeters, and, well, in the case of glioma growth, of the order of kind of months effectively. But the scaling process that allows you to go from that kind of mesoscopic to the macroscopic model is actually predicated on some scaling of space and time. And again, I'd be happy to kind of provide references to anybody that's interested that goes through those kind of deep processes in detail.
Okay, thank you very much. So now, may I request Professor Kevin Painter to stop your slide sharing?
Absolutely. Thank you very much for your time.
Okay. So this is a small appreciation on behalf of Bangladesh Society for Mathematical Biology to Professor Kevin Painter. So once again, we would like to extend our sincere thanks to Professor Kevin Painter for giving his time. And we are really honored and privileged for his presence here.
Thank you very much.
So,
thank you.
Thank you very much. So now I'd like to request Professor Dr. Mamun Mullah to conclude this session. Thank you.
Thank you. Thank you again, Kevin Painter, and I'm concluding this session.
Okay, thank you very much. So, ladies and gentlemen, now we are moving to the next session. I'm in the last session of this International E-Conference. So, the speaker, the keynote speaker in the last session is Professor Philip Kemeini. Professor Philip Kemeini is the professor of Mathematical Institute and Olpson Center for Mathematical Biology in the University of Oxford, UK. So we are really honored and privileged to have Professor Philip Kemeini in this International E-Conference. So on my personal behalf and on behalf of the Society for Mathematical, Bangladesh Society for Mathematical Biology, we would like to extend our sincere thanks to Professor Philip Kemeini for accepting our invitation. And this session is chaired by Professor Dr. Haidar Ali Biswas from Khulna University, Bangladesh. And Professor Haidar Ali Biswas is also serving as the president of Bangladesh Society for Mathematical Biology. Now, I'd like to request Professor Dr. Haidar Ali Biswas to conduct this session. Thank you. Now over to Professor Dr. Haidar Ali Biswas.
Thank you, Dr. Kobir. And first of all, I'd like to thank the audience and the participants from home and abroad. And very beginning, I'd like to express very warm good evening to everybody. So this is the last session of today's International E-Conference on recent advances in biomathematics. And I hope our audience from different countries over the globe have enjoyed, even have learned a lot of things related to their research, especially for our young students and researchers. We have learned a lot of things, a lot of research interest have been grown from our eminent speakers. So now our speaker, the last speaker, Professor Dr. Philip Kemeini, and I'd like to introduce first, very short, briefly, because Professor Philip has a long academic history and research background. Actually, it is a very short time to introduce him in this short scale in this forum. So just I would like to summarize his academic background and research for a long professional activities. The first of all, his main topics of this conference is modeling collective cell movement in biology and medicine. Actually, very important topics covering in biology and medicine. So before that, I would like to introduce Dr. Philip to the audience to know about his background. And then I think our young researchers can get more connected with Dr. Philip with his recent works and in the relevant topics. Dr. Philip Kemeini received his DPhil, Doctor of Philosophy, in 1985 under the supervision of eminent Professor J.D. Murray. Actually, J.D. Murray is very familiar in the biological field. So Dr. Philip is the student of J.D. Murray, and he was appointed the Professor of Mathematical Biology by recognition of distinction and Director of Olpson Center for Mathematical Biology, Mathematical Institute, University of Oxford, United Kingdom, in 1998. In 2005, he was appointed a statutory Professor of Mathematical Biology. He is on the editorial boards of a large number of journals, including serving as the editor-in-chief of Bulletin of Mathematical Biology from 2002 to 2015 for a long time. He has also been an elected member of the boards of Society for Mathematical Biology and European Society for Mathematical and Theoretical Biology. He is the fellow of IMA, Institute of Mathematics and its Applications, a Siam Fellow, an inaugural BSMB Fellow, a Fellow of Royal Society of Biology, a Miembro Correspondent, that is Foreign Fellow, La Academia Mexican de Ciencias. In 2015, he was elected Fellow of Royal Society. And in 2017, he was elected Fellow of Academy of Medical Sciences and Foreign Fellow of the Indian National Science Academy. Dr. Philip conducted a lot of research projects. His present research projects include the modeling of avascular and vascular tumors, normal and abnormal wound healing, and a number of applications of mathematical modeling in pattern formation in early development, as well as the theoretical analysis of the mathematical models that arise in all these applications. He has over 300 publications and also held in visiting positions at a number of universities globally. He was a distinguished foreign visiting fellow in Hokkaido University in 2002. He was appointed as a distinguished research fellow at the African Institute of Mathematical Sciences, South Africa, for 3 years. He co-authored with Jonathan and Paul a Bellman Prize-winning paper in 1997. He was awarded a Royal Society Trust Senior Research Fellowship for 2001 and 2002, and a Royal Society Wilson Research Merit Award from 2006 to 2011. In 2009, he was awarded the LMS Lever Prize and Lectureship, and in 2014, he was listed in the world's most influential scientific minds 2014. He was ranked by Thomson Reuters. In 2017, he was awarded the Arthur T. Winfrey Prize from the Society of Mathematical Biology. So this is a very brief introduction about Professor Maini. Now I would like to request Professor Maini to present his beloved speech to this audience. So please, Professor Maini, now you can present. You just share your presentation to our global audience. Thank you, Professor Maini.
Okay, well, thank you. First of all, thank you very much for the kind invitation, and also thank you for the very kind introduction. And so I'm going to talk about modeling collective cell movement in biology and medicine, and make sure this works. I'm going to start off by just talking about what collective behavior and collective movement means. And many people will have seen the spectacular videos on YouTube of birds flocking together, of fish schools. And in fact, you might even have seen these in real life. And also you see collective behavior in animals, in wound healing, and in cancer. And so why is it important to understand collective movement? Well, it's basic scientific curiosity. Why do organisms move collectively, and how do they move it? How do they do it? And if we could understand how they do it, then that might help us to understand when it doesn't happen in context, when it should happen, for instance, in developmental biology and wound healing. It may also help us to stop it from happening when we don't want it to happen, for example, in cancer. So this talk is only composed of 2 parts. The first part is going to be neural crest, and I'll explain that soon. And that's going to be very much linked to the biology. And then the second part of the talk is going to be more theoretical, looking at something called leader-follower behavior. So first part is going to be cranial neural crest cell migration. So this has been work I've been doing for the last decade in collaboration with experimentalists at the Stowers Institute for Medical Research in the US, in particular, Rebecca McLennan and Paul Kalesa, and with my colleagues Ruth Baker and David Kay, and with a few generations of graduate students, Louise Dyson, who's now faculty at Warwick, Linus Schumacher, who's now faculty at Edinburgh, and Raza Ginuati, who's in the process of writing up her thesis. So what is neural crest? So neural crest is a structure, transient structure in vertebrates that give rise to many of the major structures in our body. And there are 4 neural crests: cranial, trunk, enteric nervous system, and cardiac. And we're going to focus on cranial. And I should mention that many people have worked on this. And in fact, Kevin Painter, previous speaker, has done some very seminal work on this area, looking at a certain model of neural crest invasion. So here's a cartoon. So this is like the head of the embryo, and this is the tail, and this is the backbone. And cells come out of the backbone or neural tube, and they migrate to positions where they're then going to form structures. And if you look at a cross-section sort of through the body, you see the cells coming out like this, and they have to migrate to these regions here. Here's an experimental image. So this is a chick, and this is the head, and this is the tail down here, and this is the backbone. And here are the cells in this yellow color emerging and collectively moving to where they want to be, where they have to be. We're going to be looking at cells that come out from this place here. This is called rhombomer 4, and they migrate to branchial arch 2. And this will give rise to the structures, amongst other parts, that are in your jaw, in the lower cranial part of your body. So why is it important to study this? Well, it's very important, crucial for proper development of face and neck. Neural crest in general, there are 66 birth defects that arise when the neural crest does not behave properly. And the cranial neural crest are very similar. In fact, many, like melanoma, for example, are derived from melanocytes that are derived from neural crest. So if we could understand the normal behavior in neural crest, this might help us to understand abnormal behavior, which happens in tumors. And crucially, this is a model system that's experimentally tractable. So now let's go back to look at some data. So here are the neural crest cells, and they're coming out. And as time goes on, you see this invasion. So this takes place, roughly speaking, over 1 day. And during that day, the domain is growing. The domain grows from, roughly speaking, in length 300 microns to about 1300 microns. And here's a growth profile, which sort of looks a bit like logistic growth. And now here are the cells. This is the path on which they're moving. And so now we're going to make some model simplifications. Clearly, this is 3-dimensional, but the 3rd dimension is about 3-cell, 4-cell widths. So we're going to ignore that. So we're going to think of it as being flat. Secondly, this is curved, but we're going to think of it as being a rectangle, a flat rectangle, a flat two-dimensional rectangle. So what we know is, well, in other neural crest, we know that proliferation plays a very big role in the movement and the pushing of the cells. But there's very little proliferation of the neural crest cells, the cranial neural crest cells. Moreover, if we just had the cells moving randomly, then we can do a very simple calculation by looking at the mean square distance to find that it would take too long for the cells to migrate. So it's been known, and again, this relates to some of the talks earlier on, there's a chemoattractant, which is called VEGF, which actually plays a big role in cancer. This chemoattractant is a chemical that's produced by the tissue that lies above the domain. And it forms a chemical cue, and neural crest cells move up the gradient of neural crest, of the VEGF. So this transforms a random movement to a bias, random walk. So this could be this could make the cells migrate in time and get to the end of the domain more quickly than just using diffusion. So the model hypothesis was that the neural crest cells come out of the neural tube, they consume the VEGF, that creates a gradient, they move up that chemical gradient and invade the tissue. So this is the hypothesis we're going to test. So a mathematical model for the chemoattractant, dc by dt. So this is diffusion, and we scale the domain to be 0, 1. And since the domain is growing in the x direction, we get a 1 over L squared. The form of this is not important. This is just a simple curve fitted to the data of the growth. Since it's a growing domain, we get this dilution term in here. We have a production term of the chemical, and then we assume that the cells, which are going to be individual particles or disks, center xi, yi, we're going to assume that they consume the chemical in a sort of Gaussian way, that the consumption rate quickly goes to 0 as you move away from the center of the cell. So this is the simplest possible PDE to describe the dynamics of the chemoattractant. Now, at PDE, we need boundary conditions. And we actually do not know from the from the biological point of view, what should the boundary conditions be? So we're going to make up the boundary conditions. And when we started this, we assumed homogeneous Dirichlet boundary conditions. Later on, we used zero flux boundary conditions. And in fact, for the particular phenomena we're looking at, the boundary conditions don't make any difference. We then model the cells as discrete entities that are excluded from each other by volume. So they have a certain volume. They randomly, stochastically sense their surrounding area. And if they see a chemical concentration larger than the chemical concentration at their center, taking noise into account, they will then move with a fixed velocity, and we know what the velocity is from experiment. They will move with a fixed velocity in that direction. We don't take into account the details of the binding, etc., because we're modeling this at a very high level cell tissue scale. Okay, so this is the hypothesis we're trying to test. So we run this movie. So the cells are coming out, these lines are them randomly sensing the chemical moving up the gradient. The chemical is being consumed and it's being diluted because the domain is growing. Cells are coming in here when space is available, and you can see that this is not working because the chemical gets used up here, the gradient is too localized, and the cells can't invade. So this simple hypothesis doesn't work. And in fact, biologically, they observe that as the domain grows, the VEGF expression does look something like this. It moves away from the neural tube. So then we said, well, this hypothesis the biologists had, we said that doesn't work. So then we said, let us suppose that the cells here, suppose they could attach to the cells in front of them, then they would move. So we said, suppose there are two cell types, cells at the front that respond to the chemical gradient and move up it, and we'll call those leaders. Cells at the back that touch the cells at the front and stick to them, and we'll call those followers. Then if we do that model, we find that we get the movement to occur. So the white cells are the followers, the yellow cells are the leaders. So what this model suggested was that these cells have different type. They're not all the same. So we went to our biology collaborators and we asked them, are the cells all the same? And they said, we don't know, but we'll do some genetic analysis and tell you the answer. So they did genetic analysis they split the domain into 4 because experimentally that's the best they could do. And then they analyzed the gene expression from cells in each of these 4 domains. And they did bioinformatics analysis. They found that in fact, the cells are different. As you move along the stream, they express different, they have different gene expression patterns. In particular, what they found was that cells at the front that we would call leader cells express genes that are to do with guidance and navigation. And in particular, they express a lot of genes that invading cancer cells express. And what they found was cells at the back, the ones we call followers, express cadherin, which makes them sticky, which is what the model predicted that they would do. So then we did a lot of work with them, and I'm only going to present some results, where we meet with them, we decide what experiments can they do in the lab that we can do on the computer, and then we meet and compare our results. So there's a number of results of experiments that agree with the model. I'm only going to present one of them here. What happens if you take away the followers? So the mathematical model predicts that the leaders will stretch out very long here. And here's the experiment, and the leaders are stretched out to here. These in red are the leaders. These are normal in the blue. Normally the leaders would be more dense. So here, the mathematical model agrees with the biological model. Here's a more interesting experiment. What would happen if you took followers and put them in the front? The mathematical model predicts that if you put the followers in the front, then the followers have no guidance cues now because there's no leaders near them. So they will just be advected by the domain growth. And that's wrong. That's not what happens. Here's the experiment, and here are the transplanted cells in red, or sort of purplish color, and the blue are the host cells. And what you see here is that the followers are actively migrating. So what it seems to be happening here is the followers have changed type and they've become leaders. They've changed their phenotype. So to test that model, to test that hypothesis, we did the following experiment. And here you don't need the mathematical model to figure out what the result is, but we did it anyway. What would happen if you put some chemoattractant, a source of chemoattractant, along the pathway? Well, the mathematical model now says the leaders, they'll continue to move in response to the VEGF that's already there. The followers will become leaders because of the high concentration of VEGF and will move towards the VEGF. So that what you will get will be a breakage of the stream. And that's what happens. You get a clump of cells here, and the rest of the cells moving on. So the next question they asked us was, how many leaders do we need for successful invasion? And our model is too crude. We can't get good parameter estimates. We can't really answer this question quantitatively, but we can answer it qualitatively. We can answer the question, what would happen if you increased the number of leaders? So here is normal in the mathematical model, and here is mathematical model prediction of what would happen if you increase the number of leaders. So if we look here, this is the normal one, and you invade the domain. Here is when you increase, make more leaders. So the model prediction is you will invade the domain, but there'll be fewer cells. Here is the data, normal case, invasion. Here you increase the number of leaders, you get invasion like the model said, but you have fewer cells like the model said. But look, the numbers here, the scales are different, so the numbers don't match up, but we didn't expect that to happen. So there's a number of open questions here, and I'm going to just address one or two of them because of time constraints. Now, one thing that we know is that biological systems have more than one way of doing things. So there must be more communication going on between leaders and followers other than just sticking. So could they be creating chemical signals? Could they be doing a mechanical interaction like the last talk when Kevin gave and showed how due to realignment of the matrix, you could get paths going? Or could it be that they create tunnels, that the leaders make a hole through the tissue through which they're moving, and that makes it easier for the followers to follow. So it turns out that what our colleagues found was that the leaders, they upregulate this water channel called aquaporin 1. What this does is it stabilizes Philopodia. So for example, in our mathematical model, we had the cells randomly sense and then move in that direction. What this means is that once they've sensed a direction to move, they don't then randomly try to find another region. They continue moving there for a length of time before they sample again. And it makes them create tunnels. So here's a video. So this is an experiment done in a dish. Here is a normal neural crest cells. Here is where you downregulate aquaporin, and here's where you upregulate. And what you can see here, there's greater directed invasion here than here, and there's more directed invasion here than here. So now we make our model more complicated by putting these extra factors in. So we have that the leaders do not have more inertia in terms of if they sense the gradient, they move longer in that direction before they try to sense again. And we have that they create a tunnel for the followers. And you see that here's normal, here's when you upregulate the aquaporin, here's when you downregulate the aquaporin. So this is consistent again with the experiments. Now there's some other open questions, which are, what should the boundary conditions be? How are the cells confined? And in fact, to date, what we know is that the cells are for 200 microns, so that's roughly speaking 1/5 of the domain, we have found a chemical that stops the cells from moving away from the corridor. But after that 200 microns, that boundary is no longer there. So we're actually in the process, literally this week, the students started to do simulations asking the question, if you have a confinement only over part of the domain, is that enough to get the cells to move in the corridor? Second question, simplification in our model, is that we said there are only 2 cell types. In fact, it turns out, as we saw, there are more than 2 cell types. So a very nice paper by Linus Schumacher has looked at how you could have an activity variable. So you could have a continuum of cell types with a continuum of a continuum in terms of how they respond to other cells, how do they respond to the gradient, and you can get the invasion. More recently, we've been looking at the domain growth profile. So what we found was that the domain grows, we had it growing uniformly in space, but non-uniformly in time. In fact, what happens is the domain growth is non-uniform in space. It does not grow uniformly in space. And the growth of the domain occurs due to mesodermal cells that are in the domain they divide. We found that their division rate is influenced by the neural crest cells. So the neural crest cells are coming in, they are stimulating the mesodermal cells to divide, and that's causing the domain to grow. So these are all projects that we're actively looking at the moment, but I'm not going to go into the detail of those. Each one of these requires a more sophisticated development of our model, extension of the model, I should say. So what we found here in terms of this collective sort of stream formation is the idea that all the cells cannot be the same. The simplest possibility is leaders and followers, but you can expect there to be different types of cells present. You can change your type, and in fact, there's complex interaction between the cells in the growing domain, and this DAN is the chemical I mentioned that's expressed next to the neural tube that starts to confine the cells. So this phenomenon of leaders and followers occurs in animal movement, and it occurs in tumor dynamics. In tumor dynamics, you have leaders and followers. So it's a common phenomenon. And I should just mention some review articles here we've done on the neural crest. And now I'm going to move to the more general phenomenon of how do you model leader-follower behavior. And this is stimulated by something actually Kevin just mentioned about vasculogenesis, the formation of new blood vessels. So the formation of new blood vessels, obviously it's extremely important that we have a vascular system. Moreover, when we get an injury or a wound, then our blood vessels are damaged. They have to be repaired. In tumors, when tumors begin to grow due to their excessive metabolic demands, they need more nutrients, and they create their own vasculature system, and that's called angiogenesis. And this is work with a former graduate student, Samara Pillay, and my colleague, Helen Byrne. So here is just a cartoon of angiogenesis. So here is a tumor. When the tumor needs more nutrient, it actually produces some chemicals, amongst which is VEGF, the chemical we've just been talking about. This chemical diffuses to the vasculature. It causes the cells in the vasculature to break off and to move towards the tumor, and you have a leader-follower behavior. In this case, the leaders are called tip cells, and they respond to the VEGF and move up the gradient. But now what we have, the followers move by dividing so that you get a tube forming. And finally, these tubes interact with each other, come together, and they form vascular structure. So as a schematic of that, here is the tumor, here is blood vessels, here are the endothelial cells, these are blood vessel cells. Here's the tips. The tips might branch, or they might come and stick to each other and that's called anastomosis. And as the tip cells move along, the cells behind them are stimulated to divide, and that forms these tubes. And this idea of movement, leader and follower movement, was first actually modeled using something called the snail trail model back in 1982 by Leah Edelstein-Keshet, talking about fungal growth. And then later on, Baldwin and McElwain and Byrne and Chaplin looked at this in the context of angiogenesis. So here, in one dimension, N are the leaders or the tip cells, E are the endothelial or follower cells. And this again relates to one of the earlier talks. We just have diffusion here, random diffusion, a simple movement up the chemical gradient. Then it's known that as you increase the chemoattractant, you get more tip cells generated. So that's that term there. This term here is when a tip cell collides with an endothelial cell, it no longer is a tip cell. And this is when two tip cells collide. And then the idea of, if you look at this thing, we know this is minus the gradient of a flux. And since it's the flux that contributes to the growth of E, the flux term is put in here with the scaling term because this is a density and these are lengths of cells. Okay. And so what we see here, so that's the snail trail model. Okay. And if you discretize this, and this is work by Anderson and Chaplin, there are many, many discrete models have been proposed. And this discrete model comes from simply taking this model here and discretizing it and putting some noise into it, and you get this movement going on here as time increases. And then you get this. Okay. So what we've decided to do is, instead of going from continuum to discrete, we're going to go from discrete to continuum. So what we did was we said, let us take the idea, the verbal ideas I've just proposed, and let's write them down as a discrete model. So we're going to do this on a rectangular domain, a rectangular lattice, sorry, a square lattice, I should say. So here is, if a cell is at lattice point I, j, and if it was purely diffusion, then the probability of it moving to the right would be a quarter. The probability of moving to the left would be a quarter. And then in the y direction, probability of moving up would be a quarter. Probability of moving down would be a quarter. But now we're going to introduce a bias due to chemotaxis. And the bias we're going to model very simply as a center difference. We're going to make the assumption that branching occurs perpendicular to the direction of motion. So the tip cell is moving along here and leaving behind stalk cells. Then the tip cell, when it divides, it'll divide like this. And the probability of dividing is related to the chemical concentration because that's what's in the previous model. Okay, so sorry about that coming in. So I don't know why the Skype thing keeps coming in. Okay, so when we do that model, what we get is something like this, going along like this. And then if we integrate these, we get this sort of thing here. So we get the tip cells moving along here, and behind them, the stalk cells. And in fact, this is what we want to compare to we want to get a continuum model to describe this. Okay, so the way we do that, well, the way we get this sort of thing here, because it's stochastic, is we do many realizations and then we average the occupancies. And now we try to develop a continuum model that takes this into account. Okay, so in the continuum model, so this is a very standard sort of thing. We say, suppose we're at I comma j, then how does the occupancy at I comma j change? Well, it could change. A cell could be in a neighboring part of the domain, and then it could move with this probability to that square. Or it could be in another part and move backwards. Or it could move down, or it could move up. Okay. Those are pluses, and then the minus. Sorry, I don't know why the Skype thing keeps coming. Or it could move out of the domain of that region. We get these things here. And then we do this for tip-to-tip anastomosis, et cetera. It all looks very complicated, but it's all very, very simple, very straightforward. And then what we do is we then expand these in Taylor series, and we take the limit. And what we find is for N, which are the tip cells, we get this equation here. And for E, which are the stalk cells, we get this equation here. And now we can relate these macroscopic parameters, like the D, chi, etc., to the microscopic parameters, probability of movement, probability of division, probability of movement. Like this is the typical diffusion limit you get here, where tau is the time step and h is the spatial step. Okay. The boundary condition is zero flux, same as usual. And to get a one-dimensional description of this, we simply average, if we go back here, we simply, since the original snail trail model was in one dimension, we simply sum up along here, integrate along here to get this one-dimensional picture. And that's what we do here. Okay, so we do all of that. And what we get is this model. And if you look at this model and compare it with the model, the snail trail model that we'd all been using. Now, if you look at this equation here, these terms are the same, n squared, ne, nc, they're all the same. This term is the same, but look, we've got this term. AN and AE are parameters. And we see, and these are all normalized densities to lie between 0 and 1. So we see that the snail trail model that was proposed to describe that verbal model, when we actually take that verbal model, write that verbal model's rules out, coarse grain, and get a PDE, we do not get the same PDE. And we could argue that since N and E are less than 1, and these parameters AN and AE are less than 1, we could argue that this term here and this term here are small, so maybe this is 1. So maybe this is a bit like this equation. But look at this equation for E. It is completely different to this equation. So the take-home message of this one is that when we take the verbal model for this snail trail and we coarse grain in a systematic way to get a PDE, we get a completely different PDE model to the model that we've all been using. And when we do this, because we do it in a systematic way, we see the assumptions that had been made implicitly in the previous model. And one of the most important assumptions here is that there's been a lot of mean field approximations being made, and spatial correlations have been ignored. So we now have 3 models. We have the cellular automaton model, the snail trail model, and this new continuum model. Before we compare them, one thing I have to point out is that this model here, when you go into 2 dimensions, you have to take into account the fact that you have movement like this, and it turns out that you have to put this extra factor in here. And this is in a paper that was just published actually earlier this week. So we now compare these models. And here's a comparison where the black, remember, is the the discrete model, which is sort of like the true model. The red one is the snail trail model, and the blue is the new model. And look, they all sit on top of each other. Here's another comparison where the PDE and the ODE, or the 2 PDE models, do not agree with the discrete model, but they're identical to each other. So these 2 PDE models that are completely different to each other are giving identical results. So, and that really surprised us. When we got this new PDE model, we thought it would behave in a different way to the PDE model we've all been using, but we found that they gave results very, very similar. So what we've been doing recently, and this is in a paper submitted with graduate student Duncan Martinson and our Japanese colleague, Kazu, is we've analyzed now these continuum models and tried to understand why do they agree. And I'm not going to go into the details of that, but what we've done is we've identified 2 very important parameter groupings. This parameter grouping here, which is diffusion of tips times branching rate over the chemotaxis coefficient, and this parameter here, branching rate over tip-to-tip anastomosis. And what we found is that if these 2 parameters are small, then we can show that the 2 models agree to first order. And we can find analytic solutions, in fact, to the problem. So the importance of that piece of work is that, first of all, how we can go from a discrete model to a continuum model, but that depending on how you do that, whether you do it in the way we did it, which was in a coarse graining, but in fact, if you did a different coarse graining processes, you would get different models. So at the moment in this field, we have many, many different models for the same thing. And what's lacking in the field is comparing those models. Because if you've got different models for the same thing, you should be comparing them mathematically. And what we've done is began that by trying to compare these two models, the classical snail trail model for angiogenesis and this new model that we've developed. We found under what conditions they do compare and they agree with each other. And we found under what conditions they don't agree with each other. And so now the question is, when you see a biological system, can you decide which model to use based on those based on those studies? Because obviously the classical snail trail model is much simpler to use, and we really want to use that model if we can, and it's been very well studied. So crucially, one of the big challenges in the field is to ask the question, how sensitive is the behavior of the macroscopic model to the assumptions made at the microscopic level? And what we've shown in this study is if these parameters are small, then the models are not sensitive and you can use the simplest model. But the question remains, with more complicated models, can we do the same thing? So what I'll do is I'll stop there and thank you for your attention.
Professor Haider Ali Biswas, please unmute your audio. Professor Haider Ali Biswas, please unmute.
Thank you, Professor Dr. Philip K. Maini, for your very influential, contributory, and very fundamental topics for our audience and for our researchers. Actually, the very challenging is the fact that human ecology or human body cell pathogen interaction actually very complex nonlinear phenomena, and depending their progression inside the body, actually mathematics can help to develop such model to describe the phenomena. But one of the most challenging topics is that to collect the real data actually to feed the model. So this is the very big challenging, especially here in our country, especially because real data collection is actually very we have a limitation here. So how can you address to collect such type of data to feed in the model to predict the real situation, what happens inside the body for the cell and cell or pathogen interaction? So please suggest your valuable comments on that. How can our young researcher can proceed in this area?
Yeah, I mean, that is a very, very good question you've raised. And as you've seen in the three of the talks today, all have had links to experiments, and experiments have been set up to try and help validate the model or to provide experimental hypotheses for the modeling. So you've seen those in these talks today, and that is very different to, if we were giving these talks 30 years ago, that would not have happened. It's only quite recently that the modeling has really integrated itself in this way with experimentation. And I would think that the key thing is that if you're coming from an environment where it's not so easy to get collaborations, for instance, with my collaborations, I'm on a lot of stuff for actually people in America. They're not with people in the UK, because the experiments the people in the UK are doing are not related to what I want to do. And how I got these collaborations going was simply from interacting with people at conferences, talking to people, looking at people, reading people's papers, getting in touch with people, etc. And it takes a very, very long time to develop these collaborations that can be fruitful. Because if you think about it, the biologist has got to be doing a problem that they can do experiments on, and at the same time, the mathematician has got to be able to address the same problem mathematically. So the chances of those two things happening at the same time are still very small. And then you've got to meet. So what I would suggest is to try and make as much contact as you can with experimental people and try to keep those contacts going. And do not expect that after one meeting with an experimentalist, you will start working together. It could literally take 10 or 15 years of interaction before you write your first paper together.
Okay, thank you so much for your very valuable suggestion, advice for our young researcher. So I think we have some questions from the audience. So now I would like to request Dr. Kabir to conduct the question answer session.
Thank you, Professor. Thank you, Professor Haider Ali Biswas. So, Professor Maloy Banerjee wants to ask a question. Professor Maloy Banerjee, please ask your question.
Hello, Professor Moini. Hope you're doing well. Yeah, hi. I am just wondering, it is an excellent talk and I follow your all the works all the way, but I'm just wondering, are you planning to extend this work in three-dimensional space also? Because embryo and entire growth is three-dimensional, and I can understand that computational cost is very high, because once you are working over a growing domain, it is very difficult to somehow accommodate all the technicalities within 3 dimension. But I'm just wondering whether you have a plan to extend it to 3 dimension or not, just to understand how different kind of bifurcation is taking place, to understand different formulation of organism of different parts. I'm just, that is my curiosity.
Yeah, so the thing is that, so we haven't done, so you're talking about the second part of the talk. And the 3-dimensional thing is a really, really good point, because in the second part of the talk, in these models for angiogenesis, modeling them in 2 dimensions is not a good thing to do, because in 2 dimensions, 2 lines will almost always meet with each other. So you will get loops forming, which is what you need for blood supply. But in 3 dimensions, 2 lines will almost always never meet. So as soon as you go to 3, so if you model angiogenesis in 2 dimensions all the time, you miss a really fundamental problem, which is in 3 dimensions, when you've got 2 branches going like this, why don't they miss each other all the time? Well, okay, they'll have a volume, so that will help. But in fact, it turns out that when they get close to each other, they must be able to signal to each other so that they will not just go like this and miss each other, they will actually go up to each other. And this is where something that Kevin talked about becomes very important. As they're coming along like this, the mechanical interactions, because they're moving through matrix, they're deforming the matrix, they're setting up mechanical signals, and you can imagine cells coming like this, aligning the matrix in this direction, and then moving up. So the three-dimensional aspect, as you pointed out, is really, really important in this. And we haven't done it yet for all the reasons that you've
Yeah,
mentioned.
that's true. Because
very important.
Because in your paper in 1995, as you have mentioned, that once we move from one dimension to two dimension, so just stationary Turing pattern can be converted to either spot or spot and stripe and labyrinthine, and even spot and labyrinthine in two dimension cannot be captured separately in one dimension. And you explained nicely in your physical review paper in 1995 that I can recall. So that's why I asked this question. Okay, thank you very much. Thank you very much. Take care. Yeah.
Right, you too.
Thank you. Dr. Katrina is here. Maybe Dr. Katrina wants to ask a question. Dr. Katrina, are you here?
Yes, I'm here. Yes.
Yes, please ask your question.
Hi, Philip, and great talk as always. Thank you for that. Regarding switching from a discrete to a continuum model, you mentioned this particular case and two non-dimensional parameters that allow you to find that the leading order of the more complicated one coincides with the previous one. Can we hope for a different kind of system, like mechanical systems, for example, to have a kind of framework, like what non-dimensional parameters we could perhaps consider in order to guide us about the sensitivity you mentioned from the microscopic to the macroscopic model?
Yeah, so I haven't thought about that, Katrina, because I think that while there are a lot of techniques, so there are a lot of techniques available for parameter sensitivity analysis, so that, a lot of statistical techniques available for how sensitive is your model to parameter values. What is not available at the minute is functional sensitivity, because you might model something with a square term, I might model it with a cubic term, and we could both have the same reason, we could both have very good reasons for doing that. So then the question is, and somebody else might model it somewhere else. And I think that's one of the big questions for mathematicians at the minute, is that if we have different functional forms for our models, so two models with different functional forms, under what conditions do they give the same behaviors? And even though our model, the two models we looked at there, the models for E looked very, very different. But under these small parameter values, it turns out that at first order, you can integrate one of the equations so that it ends up functionally having the same derivative and the same form as the other equation. But if you had a completely different type of function and you couldn't sort of get rid of that in some limit, in some way, then that's an open question as to how you could then say, are these things similar to each other? And I think that that is a big mathematical question that it would be lovely if more people looked at that, because I think that's really important.
Okay.
So the short answer is I don't know, but I think a lot of people should be looking at trying.
It's very interesting. Yes, yes. Thanks. Thanks, Philip.
Thank you very much. So we are taking one or two quick questions. If you have, please, you may ask. We can receive one or two quick questions. If not, then we can. So once again, I would like to thank Professor Philip for his wonderful talk, and especially for giving his time to give a talk in this conference. And we hope we will invite Professor Philip again to visit Bangladesh and to give an invited talk in near future. And let me share an appreciation on behalf of the society.
Okay, well, thank you.
So
Thank
this
you
is
very
a small appreciation on behalf of Bangladesh Society for Mathematical Biology to Professor Philip Maini. It's really we are really honored and privileged to have Professor Philip Maini with us today. So once again, I'd like to thank him for his wonderful talk.
Okay, thank you. Thank you again for the invitation.
Okay, so now may I request Professor Philip to say a few words to the young researchers, those who are going to start their research in the field of mathematical biology. Just a few words and suggestions for the young researchers, those who are thinking to research in the field of mathematical biology.
So I think that, first of all, of course, I'm biased. I think you made a very good choice by coming to work in mathematical biology, because it's a very, very exciting field, and it raises questions that are very much very, very different. I mean, if you think of how mathematics, applied mathematics is developed, it's developed in an engineering context, in a physics context, and biology is much more complicated. For example, biological systems grow, and we don't have, or we have very, very crude mathematical description for how things grow, because we didn't need it before, because an airplane doesn't grow as it's flying, your car doesn't grow as you're driving it, so we didn't need these things. Also, the link between biochemistry and mechanics is another thing that requires a lot of work. And also, as mentioned in Kevin's talk, you've got this multiple scales all interacting with each other. So what mathematical biology is doing is it's throwing up very new modeling questions, and as a result of that, very new mathematical questions. And what I would suggest that you do is to sort of, if you're going to work by linking with biologists, then as I mentioned, try to start working with biologists. One thing I would say is that if you see an experiment in one biology paper, do not assume that the experimental results are robust. If you're going to build the next few years of your modeling career on a piece of biology, make sure there are a number of different papers from different research groups that get that same biology, so that you can say that biological result, that piece of biology I'm going to use, is trustworthy, it's robust. Then the other thing I would say is that be careful and take your time out of over deciding which problem to look at. There's so many different problems in biology to look at. And I would say the most difficult thing in research is getting the right problem. And by that, I mean a problem that is interesting, relevant, and tractable, that you can do something with it. And to do that, you need to think about things and seek guidance from more senior people. But I think first and foremost, mathematical biology is a very, very exciting field. It involves advances in applied mathematics. There's a lot of pure mathematics that is now coming into mathematical biology in terms of things like geometry, network theory, topology, etc. The angiogenesis stuff I talked about, there's a lot of topological data analysis on that. Mathematical biology is extending the field of statistics. It's extending computational fields. Almost any area of mathematics, statistics, computation you can think of has some relevance to biology. So it is a hugely exciting field to be in, where you can see lots of different areas of mathematics coming together and advancing science. So good choice.
Thank you very much for your inspiring speech. So before finishing, I would like to take some feedback from the participants, from one local and one international. So I'd like to request Professor Maloy Banerjee to say a few words regarding this conference. Professor Maloy Banerjee is here.
Yeah.
So please say a few words.
Yeah, it is my honor to talk towards this valedictory session in online mode. I first congratulate all of you, the organizers, to have a very good choice of speakers. And mainly, I'm very much delighted that within this difficult time, I can see some of my friends like Professor Philip Moini, Alan Hastings, and Simon Levin, whom I met several times at different parts of the world. And I just want to add one point, as Philip has mentioned, that in-depth knowledge is required. And another thing is that students should go through some fundamental and recent books published by several people who are in this conference, because I can recall the recent book written by Philip with Sergey on mathematical details behind biological inventions. So such kind of books is very much important, apart from the classical books by J.D. Murray, Mark Cott, and proper understanding of the problem, and to decide whether the appropriate techniques they have learned and going to apply. And also a thorough literature review is required just to understand from where the problem is originated. And then depending upon the recent development, students can decide how we can modify. And as Philip has mentioned, that obtaining result, that means viability of the result or robustness of the result, is very much important. In different paper, we can see people have proved, okay, there is a this kind of bifurcation. But the question is that, is it generic in nature? So if I going to change the functional form, as Philip has mentioned, instead of x squared, if I change to x cube, whether the same properties will remain there or not. And there are a couple of papers people have started working on it, like Bob Cui and others, that is structural sensitivity or sensitivity of the mathematical modeling outcome with the functional form of the system. One can say, okay, this is some sort of Rosenzweig-McArthur model holding type to functional response. But who have guaranteed that functional form should be of the form alpha x by beta plus x? It might be a good idea to have a general result such that function satisfied a particular class of properties. And that's why functional analysis, topology, and geometrical construction is coming up. And time scale, then another approach is also very much popular, that is cellular, that means discrete model to continuous model, or individual models to collective models. Those are new emerging areas for mathematical biology, as per my understanding. I am not an expert. I'm still a keen learner of the subject. So this is my opinion, and thank you very much for arranging such a excellent conference with the choice of various experts in different branches of mathematical biology. Thank you very much.
Thank you, Professor Maloy. Now I'd like to request for giving a feedback from the local participant. Professor Shomir Kumar is here. Professor Shomir Kumar Bhomik. Maybe he is not. Okay, so Professor Haider Ali Bishwas.
We can take we can take some other feedback in some other countries like Iraq or one or other parts not in our territory like India, Pakistan, Bangladesh. Is there any other one? Some is Iraq, some or USA, Morocco. Like we have a lot of participants from the different countries. Is there anyone here in the right now?
Yes, yes. Hello, sir. Hello.
Okay.
Yes.
So just
yes, myself. Yes, myself, Siddhartha Chatterjee from India, West Bengal, Kolkata. Good evening to everyone.
Okay. Good evening.
Okay. Okay. Hello. Am I audible to you?
Yes. 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 You are audible.
So first of all, I would like to thank all the respected speakers for giving such outstanding lectures in this field, mathematical biology, and also the organizers. Okay, for organizing this type of excellent event. I have gathered lots of knowledge from this conference. Okay, so thank you so much, sir.
Okay, thank you very much.
Thank you. I think here I see the Khaled Saad. Khaled Saad, are you hearing me?
Yes, yes, I hear you.
Okay.
Thank you very much. This conference is very interesting. And also at this conference, I'm very glad to see you, Professor Philip. I contacted with him when I am preparing my PhD in Cairo University. Thank you very much. It's very interesting, this conference.
Thank you very much. I think we can finish. So now I'd like to request Professor Haider Ali Bishwas to conclude the session and finally to conclude the conference. Thank you.
So thank you everybody. Thank you again. And actually, in this 2 days long conference, long time staying on the online Zoom platform. So I'd like to again to thanks all our participants from home and abroad who are attentively listening the valuable talk presented our eminent speakers from different parts of this world. Actually, we know we are facing critical time now, especially due to climate change. Our planet is facing a lot of hazardous problem, not in the ecosystem, also in our everyday health hazard. So all these changing phenomena can be captured actually in mathematics, because mathematics can capture only these changing phenomena, and it is possible to address all these issues using mathematics. And this mathematics actually acts in the interface of biology and medicine. So I would call all the mathematician, biologist, and physicist to work together to overcome the situation for a sustainable world for our next generation. So hopefully in the next time we could meet in near future after the ending the corona situation, because due to this corona pandemic situation we are very much restricted in our home. Especially we cannot move forward, we cannot travel internationally. So this is actually the only way to gather and to meet our eminent researcher, scientists in online platform. So hopefully Bangladesh Society for Mathematical Biology in the coming year we could arrange a huge gathering participating from different parts of the world physically, and the corona situation will turn out soon. And I think our eminent speaker here from 7 eminent speaker for today's international conference, we will invite all of the speakers physically to visit Bangladesh, and we hope to work internationally and to engage our young researchers, our young colleagues, our young students for being connected with these eminent speakers from a global perspective. So, saying that, I would like to conclude here for the today's international conference, and I would like to thank our media partners who have broadcasted the news, circulated the news, global print for the printing, online, and even the electronic media. And again, from the participants all over the world, especially from about 20 countries, from the participants have attended this online conference. I would like to again thanks all of them, and I think we should get in touch with our eminent speakers by sending email or contacting them, and we can make a better world for our next generation. Thank you, everybody, and I would like to conclude the session here and conclude the today's international conference here. Thank you, everybody, and stay fine during this pandemic situation. Thank you, Rob.
Thank you very much. Thank you, Professor Philip, Dr. Katrina, and Professor Painter for their wonderful talk, and Professor Kim also. And I had an opportunity to meet Professor Philip last year in Oxford in the celebration of his 60th birthday. Maybe after this pandemic, we may meet anywhere of the world. Okay, thank you very much. Thank you all. Thank you all participants for different corners of the world. Thank you. Stay safe and stay fine. And good night.
Thank you very much. Thank you very much.
Thank you so much.
Thank you, sir. Thank you, Philip Maini, sir.
Thank
you.
Thank you, sir.
Thank you.
Our feedback form, sir.
Thank you,
Feedback
sir.
form is already
Feedback
online.
form link has already been given in the chat box.
Chat box you have given, sir. Can you send it to me through mail, sir?
So just now, yes.
May I get the email list?
Sorry?
I mean, conference is over. We are organizing another conference in our
Yes.
department to celebrate the centenary. May I get
see.
the email list? So once we are ready, we can send email. We can invite.
Yes, sure, of course.
Yes, of course.
So please email me the list of.
What is the topic, sir? Sir, can you tell me any topic regarding this conference, new conference?
You can sound, I think a little bit, you can declare here what the conference, regarding the conference.
We are not ready.
Yes.
I will declare
very soon
electronically. I mean, I will email everybody. It's
Okay.
about, it is to celebrate the centenary of the Department and University of Dhaka.
Okay,
We are going to organize a conference, 2-day conference. It will be virtual one like this one.
Can you give me a clue about the topic of the
No,
conference?
it is covering almost everything. I will send email. Writing detail.
Because
What is the tentative time, date and times, like in January, February or March?
April 10,
On April,
10, 11.
okay.
April 10, 11.
And here it is our plan to cover everything from mathematics, like algebra, analysis, numerics, maths, biology, modeling.
All
because
branches of mathematics.
Yes, sir, because we are young researchers now. So we are very interested in research. We are